Welcome to the tutorial session for graph machine learning with missing multimodal information. Those of you who are joining us online, you are most welcome to engage with your organizers and each other in the tutorial discussion of the Slack channel provided. And the session will be 2.5 hours long until 2 p.m. Although there isn't another event following your session, please do end on time. Thanks. And for those of you who are unable to join or who would like to rewatch the session in the future, the tutorial is being live streamed and saved to our YouTube channel. And so, with no further ado, I will hand it over to our tutorial organizers.
Okay, thank you very much, and thank you for being here. So after the lunch break, I'm Daniele, and I'm going to also this tutorial on graph machine learning with missing some multimodal information, and that's a tutorial prepared by myself and Fragiscos Somaliaros, and it's not working. Okay, and we are from Université Paris-Saclay, and he couldn't make it, but I'm here to present the whole tutorial, basically. Okay, so the website for the tutorial is listed here, and you also have like a QR code to access to it. And so you can find like the slides and the papers and the code that we're going to use in this tutorial. Okay, so let's get started. So first, we want to understand which are the kind of motivations behind this tutorial. So we know that multimodal graphs are almost everywhere, so we can find them in many settings and in many domains. But the point is that we might have some problem. So meaning that some of these kind of multimodal information might be missing in some specific kind of domains and settings. And the point is that how can we solve and how can we address this problem? So in the literature, so we have seen a quite high number of papers talking about multimodal graph learning, and we can see that in this chart here, and also by means of these two kind of recent surveys on the topic. And also the same goes for the problem of missing modalities in general, where we have a growing number of papers addressing this kind of task, and also two surveys talking about this topic. And at the same time, we have witnessed a large and very growing number of papers, so starting from 2020, that talks about this kind of problem on multimodal information, so with missing information in graph learning. And here we have provided a timeline of possible papers so that accounted for this kind of setting and domain. But the problem here is that none of the previous tutorials has actually covered this specific topic. So we have collected like a number of previous kind of tutorials, and none of them has done this. So with this tutorial, we wanted to bridge this gap, and we wanted to provide a tutorial on this specific topic on missing modalities in graph machine learning. Okay, so now we want to give some basic concepts on how so kind of missing information works in traditional kind of machine learning. To do that, we will use a tabular dataset, so made of some samples and some features, and we can also have a set of labels, so for one of each samples. And in real-world setting, we might have that some of these features are missing. So the idea here is that we want to find a way to first input these missing features, and then kind of use the completed dataset to make some prediction on this dataset. So to do so, we may want to introduce a formal matrix B, a binary matrix, which is used to identify where the missing values are actually placed. And 1 will just refer to the values so missing, and 0 is kind of referring to the values so that are observed. Okay. So now we want to understand which are the events and the kind of situations which might lead to the missingness of information. And according to the statistics, we can have three possible kind of processes behind the missingness of information in machine learning. And they are kind of listed here. So we want to take a look at each of them. So first, we can have the setting of missing completely at random, MCR. In this setting, we have that the missing information is not dependent on the observed values and the unobserved values, which means that they are completely kind of random. And if we wanted to make an example here, we are taking a survey and we are asking some questions to many people. And some people are not providing some specific answers. And so that's a completely random situation where we are missing some of the values of this survey. Then we have the setting on missing at random, so MAR, where we basically are missing the values according to the observed values. So which means that now we have some patterns to find. And by using the examples from before, we can do a survey again where we are making questions to some people. And so, for example, the young people will not provide any information on the wealth and on the salary. In this case, the missing information is the salary, but we are missing this information on some specific values which are known, and that are the age of the people. And finally, we have the setting on missing not at random, and that's the kind of the most complex one, where the missing information is dependent on the unobserved kind of values. And so using the same example, we are taking a survey, and now the rich people are not giving any info on their salary or wealth. So here, the missing value, so the richness, it's connected to the unobserved value, so the stuff, so that we are missing. And that's the most complex scenario to take into account. Okay. So basically, the idea is to then input the missing values to obtain a complete version of the dataset, and finally to use this completed version of the dataset to run any prediction model on this dataset. So we train and test set, of course. Okay, so some very common approaches used in the literature to input some missing values. It's so they are also pretty common, and we can find, for example, the mean on the median of the values. So here we just take the mean or the median of the observed values, depending on kind of variables so that are continuous or categorical. And then we can do a KNN approach where we basically take the mean or the median of the observed values, but by first clustering the samples which are most similar to the one that we are considering and that we want to take an input on. Then we can have mice, so that is doing a kind of more refined strategy, where we first input by means of a mean and median, and then we want to take a refinement of the kind of imputed values by means of an iterative process where we train some regression models, and we do that by n number of times. And finally, we have a whole family of autoencoders that can be used to generate the missing values. One traditional method is the denoising one, where we put some noise on the original data to fake the missingness of some values, and then we want to kind of reconstruct the input data by means of this architecture here. While a second one is the variational one, where we want to train a generative model to create a Gaussian distribution and to generate the samples which are missing from the original data. Okay, so that was a kind of a very short, a very quick kind of overview on the whole setting of the missing information in traditional so kind of machine learning. Now we want to take a look at the tutorial overview and how it's been structured. So we will have a big part on the missing some multimodal information in graph learning that is going to be structured into 3 subparts. So first we will see how to handle and how to define the missingness of information in unimodal graph machine learning. Then we will see how to define and which are the most important application in multimodal graph learning. And finally, we will see how these 2 things can be combined to define and address the problem of missing some multimodal information in graph machine learning. Then we will have a short break, and then we will go through the hands-on session. So with 2 sessions, so on the 2 of the main so kind of applicative scenarios where we can find that the problem of missing some multimodal information in graph learning is prevalent. And finally, we will have some closing so kind of remarks and so kind of challenges and future direction for this topic and this kind of domain. Okay. Okay. So some questions until now, or it's all clear and we can go further? Because so we will go now to a pretty long part. So we want to be sure that it's all clear. Okay, I think we can go further. Okay, so first we can see how to define and how to address the problem of missing information in unimodal graph machine learning. So according to a recent survey, we can have 3 possible settings of missing information in unimodal graph machine learning, and they are so depicted here. So we can have a situation in which some attributes of the node features are missing. Then we can have a situation where all the node attributes are missing for some specific nodes, and that's the setting of missing features. And then we have the case of some edges so that are so kind of missing from the graph. Okay, so first we can define how a unimodal graph is kind of structured. So we can use like 2 possible matrices. So the first one is the matrix of the node features, and then the adjacency matrix to structure the kind of topology of the graph. And then, so once again, as done for the traditional machine learning case, we want to introduce 2 binary matrices B, one for the node features and one for the edges. So we want to understand and we want to formally define how the missingness is present at so kind of node level and edge level. For the node level, so basically, so we use a matrix where 1 will tell that that specific attribute is missing on that node, while 0 is the contrary. And for the edges, we will have a 1 where the edge is missing, and 0 so when the edge is actually seen and observed. Okay, so how can we define now the 3 cases so that we showcased in the previous slide? So for the missing attribute case, we have a set of attributes which are missing, and we can group them into the first part of the binary matrix, and then all the other kind of observed attributes which are present in the second part of the binary matrix. Then we have the case of missing features, where so that's actually a generalization of the previous case, where all the attributes are missing, and so we are missing the full feature vector of that node. So we have a complete vector of 1s in that case. And finally, we have the case of missing edges. In this case, so we refer to the missingness of the edge between the node I and the node J. We will not consider this third case for the sake of this tutorial because it's out of the scope and because so we will mainly focus on the missingness of information at node level. But so we can say that in general, this setting can be addressed by some similar kind of task in graph learning, like link prediction. So we want to predict a new link on the graph. So basically, okay. Now we can provide a non-exhaustive so kind of taxonomy of the approaches that we have to address the problem of missing information in unimodal graph learning. So we have two possible levels to define and categorize these approaches. The first one is when we want to understand if the missing information is actually on graph data or it's on tabular data, but it can be structured and solved through a graph data. So basically, we have on and through kind of situations. And then a second level of categorization is this one, where we have some models which actually work to generate back the missing information, and so they input the missing information, and some other models which work to make the model kind of robust to the missingness of information. So, but they actually don't kind of generate back the the missing information. Okay. Okay. So now we can take a look at three approaches which fall within these families of models that we considered. The first one is FitProp, and it was actually presented at LOG 2022, and it's like falling in the family of on and input. So how does FitProp works? So the model works as a pre-processing kind of phase, where we first propagate the available information on the graph until they are used to generate back the missing information on the same graph. But how does it work in a more of a principled way? So first, the authors think to sketch again the problem of missing information on graph data as a problem of feature interpolation on the graph. So to do that, they want to minimize Dirichlet energy kind of problem. But the problem is not that easy to compute in terms of kind of scalability and kind of computation, and that's why they come up with a gradient flow version, so that is like an approximation of the previous one, but more feasible to be computed. And so they put some initial condition and some boundary condition, as in all these kind of problems. So they kind of formulate this gradient flow as a heat diffusion problem, where the iterative procedure is displayed here in the slide. So at the end of the day, they discretize the continuous version of the diffusion to get this discretized kind of version here, and to find an iterative procedure for the model. So at the end of the day, how does FitProp work? So we first save the available variables into a dummy variable. Then we do an iterative process where we propagate the available information on the graph, and for each iteration we then put back the available information so that we don't lose them and we don't put too much noise into the into the model. And finally, we do that for several times until we reach a stable state of this heat diffusion process. Okay. Then a second important approach in the literature is surely GRAPE. So GRAPE, it's like falling in the kind of family of models where we do through, and then we input the missing information. So basically, the idea is that we start from a tabular data where we have some missing information, and this tabular data with missing information can be sketched as a kind of bipartite graph with the first partition as the node samples, as the samples of the tabular data, and then the features as the second partition of the graph. So basically, the idea here is that if some links are missing from the graph, this means so that that feature is missing so from the tabular data, or it's not. So basically, so the other way around. Okay. So how the methodology works then? So basically, we first so kind of initialize the node features through some dummy variables to so they are like not super informative, and we don't really want to learn them. So we just want to use them to perform the message passing. Then we perform the message passing by means of a graph sage model. And during the message passing, we perform a kind of an edge dropout to make the model more robust to the missingness of many possible features. And finally, we don't only update the node features, but also the edge features, because so we need them to make the propagation of the features. Basically. Okay. So at the end of the day, they use and they establish two possible tasks. So first one, it's a kind of an edge level prediction where we actually want to input the missing features so from the tabular data. And then also a node level prediction, so if the missing values are on the labels of the samples. And so it's, at the end of the day, so this scenario is resketched as a normal problem of link prediction on node classification on this so kind of bipartite graph. Okay. And finally, a very recent approach is PA-GCN, so that stands for so partial GCN. So where basically, so this model falls into the family of approaches so that work on graph data, but they want to kind of robustify, so they don't actually generate back the missing information, but they so just want to make the model kind of ready to work with missing information. So how does it work? So first they start from the assumption so that a solution to this energy minimization problem is actually given by the same formulation of the aggregation process in the message passing, so we generally know. Then we can put a mask on these features when we are missing some of these values. And so this means that the missing values and the mask will appear also in the final aggregation function that we consider. And so finally, they come up with a formulation of the message passing where they also consider the missing information. So they can actually perform the GCN layer without doing any other stuff, so because they are still considering the missingness of information on the node features. Okay. Any questions before we go further to the second sub-part of this second part of the tutorial? Any questions on unimodal graph learning and how to deal with with missing values on that? Okay, I guess that's all clear, I hope. Okay, so so now we have kind of understood how to deal with missing information in unimodal graph learning. Now we need the second step to get to the final point of this tutorial. So we want to understand how to define and how to use multimodality in graph learning. So multimodal learning, it's a paradigm born in 2019, and basically it takes the assumption that when learning from data and real world data, we cannot just use a single side and a single aspect of this data. So since the data it's kind of complex and it's made out of a multifaceted kind of perspective of the data, we need to use several kind of perspective and aspects to kind of describe and learn from it. And that's why we come up with the multimodal learning paradigm. Then we can find it in many domains, so that I put here in this slide. So we can find it in the healthcare or in the information retrieval, in recommendation, and in many other domains. But the point now is, why do we need to use multimodal data on graphs? And the point is, so put simple, the point is that we cannot really grasp all the possible connection and kind of relationships between between all modalities and all multimodal samples, because we are missing some possible and crucial information here. And this information can be encoded just by means of a graph topology. And that's why we do need to use multimodal information on graph data. We cannot just rely on multimodal data without using any edges and any graph structure to deal with it. Okay, so I point you basically to this very interesting survey, where the authors come up with like a blueprint of multimodal graph learning and how to define it. So first they kind of find a way to describe the existing models and the terminology and the methodology used in the previous works, which can fall into two possible families. So the first family is the family of models which use a single model, a single model architecture, meaning that we learn a separate graph learning model, one per each modality, and then we fuse them to obtain a final version of this data and to learn from it. While a second family is consisting of a model using one single architecture for all the modalities at once. And so in this case we learn all this data into one time, and then we make prediction on it. Okay, then they come up and they formulate a blueprint of multimodal graph learning, which is consisting of the following steps that we can see here in the following slides. So first, we want to design and learn some strategies which can map the multimodal content of the nodes to a shared kind of namespace. And this identify function is defined one per each modality and can be learned like end to end. But it's important to understand that at this stage, at this level, we don't really have any details on the topology for the graph. It's just a level at node wise sides. Okay. Then we have a second step where we actually want to learn this graph topology, and to do that we can make use of many similarity metrics to do that. And so this means that we will end up with many possible adjacency matrices, each one accounting for each of these kind of similarity matrices. And the connect function here is applied to the whole list and set of the multimodal content identified from the previous step. Okay. Then we have the third step where we actually perform the propagation of multimodal information on the graph. So it's actually the message passing or any diffusion process to do that on the graph structure with node features. And that's so what we do in these third steps. And finally, we want to make a combination of all these modality-aware kind of representation so that we got from the first three steps to then come up with a single fused representation of the nodes that will be used for the final task so that we want to make and pursue. Okay, so now so we've understood how to define multimodal so graph learning as a task. Now we want to show some possible applications of multimodal so graph learning in some domains of interest. So first we start from the domain of recommendation, and we see how multimodal so graph learning can be used. And we start by talking about Lattice. So that is one of the most popular and most famous approaches now from the literature. So how does it work? So first, what we want to do is to learn the similarities intercurring between the items at multimodal level. So we first compute the similarity, so the full similarity of multimodal features of the nodes, and so we end up with a different similarity so matrix, one per each modality. Then this matrix is too dense, and we want to sparsify it, and that's why the authors apply a top key approach to sparsify this similarity graph. And finally, we want to normalize it to penalize the nodes which have a higher degree instead of nodes with lower degree. Then, so what they do is to combine two versions of this similarity matrices. One is just obtained with what we have seen, and the other one is obtained through the same process seen before, but by learning a mapping of the multimodal features to a shared latent space to make the learning of the similarity matrices aware of the task we are pursuing. Then finally, we aggregate all these matrices into one to just obtain one single matrix accounting for all the modalities. And finally, we perform the collaborative filtering task and do the final task of recommendation. While a second approach is in the healthcare domain, and it's MMGL. So basically, the idea it's not that different from what we have seen previously. So here, the idea is to first map to a shared space the multimodal content of the patients into a latent space. Then what the authors do is to learn some kind of intermodal attentions to actually learn so basically the importance of each modality on the patient we are considering, and this is done by means of a transformer architecture. And then this leads to two possible kind of representations of the patients, which are the modality shared one and the modality specific ones. And finally, so what they do with these kind of features is to use them to refine the patient-patient similarity graph and to then pursue a graph structure learning task. And when we deal with the graphs, with the GCL task, of course, so what we want to do is to impose some constraint to make the graph feasible and kind of realistic to the actual properties of any graph. And that's why they impose two loss functions. So one for smoothness, and the other one is kind of a regularization for the final task we want to pursue. And then we have the overall loss, like comparing and like comprising all these terms of the loss functions. Okay. Any questions so far? So because that's the very last part of the lecture style. So before going to the Colab and to the Anson. Any questions so far? Yes. I don't know. You want to? Yeah.
Maybe I missed, but I don't think you cover any case of missing links. But I was thinking like when you started the presentation, you said, at least I was confused. Like if I give you a graph, how do you know? For the nodes that are connected, you can say like, do you have the link? Right? For the nodes that are not connected, maybe they are truly not connected, or maybe that link is missing. And I wonder like if you have ideas on how to distinguish that, or if anyone actually cares about the case where you actually know that the link does not exist.
Okay, so indeed, so that's a true question, and that's a pretty good question. And in fact, it's not like easy to understand how, if the missing link is actually missing or it's actually so not given in the graph, so we consider. And that's why probably we should take so kind of an assumption at the beginning and saying the missing links are actually missing or they are missing for some reasons, and so that's not actually missing. I guess that so there are some papers so that do both, or maybe so one of the other cases. I mean, so yes, and I mean, so for example, in the case of link prediction, you cannot really know if the missing links are actually missing or they are like so what you do is to like put a mask on the links to have a training set and a test set. So you assume that the links are not missing, but you want to mask them to have like a comparison on a so kind of a test set setting. Whereas you might have some situations where the links are actually missing, and you cannot entail anything on them. That's basically yes.
Another question is like, do you see any difference between like prediction versus imputation, right? If you say like link prediction, to me like the prediction task because all the predictions are of the same type, right? It's just a link. But if you have like features, then you wouldn't create a model to predict every different type of feature. So that's why for me it's like an imputation problem, not a prediction problem. But like, do you see any major difference between these two, or should we just use prediction models to solve imputation problems and vice versa?
I mean, there are some similarities, and in fact, if we go back to the grape model, they basically frame back the setting as a prediction task. So they create a bipartite graph. So where they so they create a bipartite graph so between the samples of a tabular data and the features, and the missingness of a link is the missingness of that feature. So for that sample, and they reframe the problem so that at the end of the day, it's imputing. It's actually means to predict on the missing links or on the missing labels. So for the case of node classification. So indeed, yes. So you can also like reframe the setting as a prediction task more than a kind of an imputation task. So, but at the end of the tutorial, I will also talk about what is best to actually impute or to maybe make a model robust to the missingness of information, and we will have like some discussion on that, and I will give you my personal opinion on how it's better and what is better between the two.
Yeah. Thanks a lot.
Thanks. Thank you. Any other questions before we go further? Okay, I guess we can go further to the very last part of this talk. So basically, yes, no, we should go even further than that. Okay, spoiler. Okay. So basically, now we have set all the useful background on how to deal and how to define with missing information in unimodal graph learning, and then how to define and how to apply the multimodal graph learning setting and scenario. Now we can mix and we can use the knowledge from the two cases to actually talk about, so first define and then address the problem of missing information in multimodal graph learning. And we will see that, actually many of the approaches we will see, they are a kind of an extension on what we have seen for the case of unimodal graph learning. Okay. So we can go back to the definition on how to define some missing information in unimodal graph learning, and we saw three possible cases. And when it comes to the missingness of multimodal information, the idea is that you are missing the complete feature vector for one or more modality for one or more nodes on the graph. So basically, if we take a look at these three cases, the most similar case to what I've just said is the central one. So the missing features case is the most similar case, so that can be generalized when we have multiple information on each node of the graph. And that's what we can define for the missing information in multimodal graph learning. In fact, by using the blueprint we introduced earlier, we can again say that a multimodal graph is a graph where we have some kind of multiple information on each node. So the node feature matrix is actually not a matrix anymore, but it's a tensor where we have a third dimension accounting for the modalities. And then the adjacency matrix, it's not a matrix anymore, but it's a collection of matrices, each of them accounting for a specific modality we are considering. Okay, and we've seen that. And here, if we want, again, to define a binary matrix to identify which are the missing values in this setting, we cannot use a binary matrix anymore, but we need to use a binary tensor, where we consider a third dimension for the modality case. And basically here, so what is the meaning and the structure of this binary tensor? The structure is as follows. We have a whole feature vector of all ones where we are missing that modality for that node. Why a whole feature vector? Because it's not so logical to think so we are just missing one of the cells of that feature vector, but so we are missing the whole modality on that case. Then we will have a whole feature vector of zeros where when that modality for that node is not missing and we can observe it. So that's how we translate from the unimodal case to the multimodal case in both multimodal graph learning and also multimodal graph learning with missing modalities. So that's how we translate the two cases. Okay, and then how can we reconstruct the missing modalities here? We can do that in two ways. So we can do by means of a reconstruction in terms of an intra-modal setting where we reconstruct one missing modality by means of the available features from the same kind of modality. So say we want to reconstruct the visual modality of one node by means of the available visual modalities of the other nodes. While a second setting is the one where we want to reconstruct a missing modality by means of the available ones from other modalities. So we want to reconstruct the visual modality by means of the textual modalities. We can do that because indeed it's not like we just have connection between nodes, but it's been like said so many times that kind of the modalities are connected and they have some kind of relationships and they are aligned in some way. So we can actually use the visual modality to reconstruct, say, the textual modality. Okay, and that's the cross-modal case. Then, as we have done for the case of unimodal graph learning, here we want to provide a taxonomy of approaches and how can we define them. So they will be, and they are very similar to what's seen in the case of unimodal graph learning, but with the difference that we say in a while. So first, we can consider approaches which work on graph data and through graph data, and the meaning is exactly the same as as the one that we saw for unimodal graph learning. Then we have a second kind of dimension where we have some approaches that input the missing modalities, or they take a robustification of the model so that they don't actually get back the missing modalities, but they make the model robust to the absence of some of these modalities, and that's similar to what we have seen in the unimodal case. And finally, when we consider the family or model, working on the through graphs setting, we can have two possible situations to deal with this kind of problem. And so what we can do is to start from the multimodal data and to create a similarity kind of graph where we have kind of links between samples, each one for each modality. And that's the first case. While the second case is the bipartite one, where we have a bipartite graph where the first partition is the samples of the data set, and the second subpartition is the set of modalities we are considering. And these are two possible approaches that we use in the through graphs setting we have seen in the previous slide. Okay. According to this, now we can define and we can talk about four kind of representative approaches from the literature. Okay, so first we see again that in this kind of setting we can identify many domains and many applicative scenarios here, and we report them into a timeline from 2020 up to the current days, where as we can see how the problem is quite active and predominant, and we see a growing number of papers being written on this topic. But now we can actually talk about the four most kind of representative approaches from the literature. So the first one is actually a model by us, and it's in the recommendation domain, and it's called IIProp, and it was submitted and accepted as CIKM 2024. And so basically, what is the idea of this approach? When we deal with the user item graph, we can have some missing modalities just on the item side. How we can deal with this? To do this, we just consider the item side, and so we take a projection of the user item graph into the item 1, where the connection between two item nodes, correspond to an edge. So if the two items have been interacted by at least one user. So now we have this item graph where some of these modalities are missing. How to deal with this? So first we sparsify the item graph, because it's gonna be too dense, and so we do that by means of a top key kind of approach. And then we perform a kind of an iterative process, so that is pretty similar to what they did in feature propagation, so the previous model, so we've seen in the case of unimodal graph learning. So how does it work? So first we store the available modalities into a dummy variable. Then we put the missing ones as zeros or any other kind of initial values to initialize this iterative process. Then we do the imputation of the missing modalities according to the item-item graph and to the available ones. And finally, we put back the available information into the proper order, and also the missing ones, so that we input it into the proper order. So this model falls into the family of on-graph and input. Okay. So how can we define the input functions? We can define it in many ways, from more simple ones to more complex ones. So first, what we could do is to leverage the item-item graph and take the mean of the neighbors at the first op. So this is like the most simple case we can think of. Then we can do a propagation at multiple ops. So we propagate the available information at multiple ops of the self node. And while we do that, we do a normalization of the adjacency matrix to make it like robust to nodes having higher node degree and lower degrees. And a third possible case is when we want to leverage a very kind of recent and kind of powerful outcome. So from the kind of NeurIPS 2019 paper, so that tells that diffusion can improve graph learning. And what we do is to make the normalization of the item-item graph by means of a personalized PageRank diffusion, and then we do the propagation at multiple ops, as we have done in the previous cases, and that's what we do in this kind of approach. Then we have a second approach, so-called MMGCAL, so that falls again into the family of on and input, and it's still for the recommendation domain. It's not that different from what we proposed, but it has some differences. And now we can consider them. We can take a look at them more in depth. Okay. So first, the model works again by considering the item-item graph, and they perform a personalized PageRank normalized propagation of the available features to reconstruct the missing ones on the item side. But what they do more is to then project through a PCA the obtained multimodal features into a latent kind of space. And finally, a very big difference is that they do the same stuff on the user side, because they consider that some missing features might be present also at user side. Okay. Then, what they do is to perform a cross-modal similarity between the between the modalities. So the visual with the audio one and vice versa. Then they they construct a similarity graph through a soft attention on these kind of modalities to finally obtain a kind of an attention matrix where so that they can finally combine with the previous so kind of formulation, so for the previous so kind of representations, and to obtain a final, complete, overall so kind of representation of that item, so from the system. And finally, they perform a node and edge dropout to improve the kind of representation of the user and the item embeddings, and to perform better the task. Okay. Then we can conclude with the very last so kind of applicative domain, so where we consider the missingness of multimodal information on graph data, and that's the healthcare one. So here we also consider two possible approaches, so kind of very recent ones. So the first one is M3Care, and the M3Care model falls into the family of approaches which perform a through graph, and then they make a robustification, an imputation of the model. So since it's a through graph, we also define a further family. So because this model is create a similarity graph between the patients. Okay, so how does it work? So first, we project the multimodal content describing the patient into a shared space of shared latent space by means of some specific modality aware function to do this projection. Then what they do is to learn end-to-end a patient-patient similarity graph by means of a deep kernel, where two RBF kernels are considered. Then, so since we are performing a graph structure learning task, we want to impose some constraints, and that's why they put a loss function to make them evident and to make them kind of coherent, so within the pipeline, so that's what we are considering. And finally, they fuse all the patient similarity graphs into one, and they perform a kind of a specification to make the overall similarity graph more sparse by means of a learnable threshold on the values. So at this stage, we have all multimodal features, and some of them are missing, and we have one single patient similarity graph accounting for all the modalities. So what they do now is to propagate the available features on this graph, but they do that by means of a GCN. So they want to learn this kind of propagation end-to-end in the downstream task. So that's different. So with our approach or other approaches, so that we have seen. Okay, and finally, they combine two representations of the multimodal patient of the multimodal content of the patient. So they and they combine them by means of an attention mechanism, where they want to learn what is more important between the original content or the one learned. So with this pipeline we considered here. Okay, and then they finally apply a kind of a transformer architecture, so where they then do the prediction at patient kind of level. Okay. While the final approach is Muse, and it's dated back to 2024, so that is pretty kind of recent, and Muse falls into the family of through graphs, and then the robustification one. And then it does apply a bipartite graph instead of a similarity graph. Okay, so how does Muse work? So Muse, it's first creating a bipartite graph of the patient nodes and the modality nodes. Then the missingness or the presence of an edge means that so that particular modality is missing or present from that patient. So what they do is to actually kind of run a link prediction task to then predict input the missing multimodal features of that patient. So in this case, the multimodal features encoded at edge level are actually the most important information we want to have. And they do that by means of a mutual kind of consistent contrastive loss, where they have an unsupervised kind of term and a supervised one. The unsupervised term is used by means of an edge dropout setting, where where we want to make the two views of one node obtained through edge dropout to be consistent. And also the supervised term is obtained in a way in which if two nodes have the same labels, the authors want the two nodes to predict one another, and that's the kind of supervised one. So Muse, in certain ways, is similar to the GRAPE methodology, but it applies it to a multimodal domain, and this performs also some kind of contrastive learning to make the model more robust to the missingness of modalities in this case. And that's it. Okay, so now we have a break of 10 minutes, and so we can have some questions if you have further questions.
Thank you for the tutorial. So at the beginning, you talking about the different missing mechanism like MCAR, MAR, and MNAR. So when you have an overview of all those different types of missing imputation techniques for the multimodal learning, does those techniques take the missing mechanisms into consideration? Like, do they perform well when the missing is missing, not at random?
Okay, so indeed, so most of these approaches here are considering a missing completely at random setting. So that's the short answer. Indeed, we could consider, and some of them also consider other settings. So for example, Muse, they also consider like a further setting, so with missing, so not at random, where they try to kind of solve the problem in this setting. I mean, for the other approaches and the other papers presented, they don't really make kind of any different kind of assumption apart from the MCR kind of setting. Indeed, so since here we also have a further a kind of a further dimension of the modalities, we might consider to extend maybe all these definitions to a case where we can also see how the multimodal data is missing in all these three settings. So we consider so at the end of the day, we could end up with more than just three possible cases of missing information, we can say.
Thank you.
We have another question from the online audience, probably regarding the contents between break 1 and break 2. So this is a two-part question from Raphael. So first, regarding missing links, he asks if the challenge you described with link is the same for nodes. Specifically, do we face the same ambiguity in determining if a node is simply unobserved versus there being a specific reason for its absence? And second, regarding modalities, in cases where different modalities aren't perfectly connected or aligned, can we use temporal information to further refine the representation after the initial learning phase?
Okay, so for the first question, indeed, it's important to understand if the missingness of information also at node level is actually linked to a missingness, so kind of process, or it's so not given for any so kind of reason. But I guess that the answer to this question it's like a more general answer, so that we might give in general so maybe not so dependently on the graph learning task. So in general, in machine learning, we might have so that the missing values are missing for a reason, or they are missing and we want to input them. So I guess that this is an assumption so that one does at the very beginning of a project, and that's like followed, and that's like kept for the whole time of the project, I would say. While for the second question, okay, so indeed we can use the temporal, so the temporal information. So because this could become like a further modality to just leverage, and also the temporal information. So could be good and important to so kind of considering. So because it might happen so that some values or some modalities are maybe so not missing first, and then so after a certain time they are missing. So that's also another important aspect to consider. And maybe if we add so this graph data to be evolving over time, we should consider also so this kind of setting, and so the temporal setting is also pretty so much important. Yes.
Thank you.
Other questions? Otherwise, we will. Oh, okay. Yes. Yes.
So this is a follow-up on the MCAR question. So how would you handle like a case, for instance, like adversarial missingness? For instance, maybe the patient that has a disease is more likely to have a missing value. So maybe you want to predict that disease. So have you seen approaches that can handle like missingness processes that are a little bit more complicated than just
I mean, but in that case, you would end up into either the MAR case or MNAR case. And in that case, you should indeed so maybe not just maybe rely on the methodology so we have seen, but we should consider more complex so kind of models, because a very big risk here is to make some imputations, but actually to put some bias into the dataset and the models we consider. So indeed, so when we deal with this kind of more complex setting, we cannot just rely on the methodologies we have seen, but so we should make some more careful so kind of modifications to the to the models, and also to the prior knowledge to better understand how to deal with this kind of setting and situations. Yes.
And another question is like, of course, if you're doing imputation, then you're probably not very sure that the value that you're predicting is the correct one. So are there ways that I can account for like that uncertainty, like as
Yes.
part of the model?
Yes, and actually, so that's one of the future work so we will talk about. So because indeed, one making some kind of imputation, you cannot really know if the generated data is correct or not, and that's why and that's why so you usually take a mask on the available features and fake the missingness of some modalities, so that you can reconstruct them and you can compare them so with the actual values so that were like hidden in previous time. So that's a possible way. So you can do that. So, but you should do that. So because just inputting and not being able to see if the inputted data is correct and is high quality or not, it's like pointless. And maybe you might have some improvements on the final prediction task, but it's not due to the imputation you did. So basically.
Thank you.
Thank you. Thank you. Other questions, or should we have a quick break?
Yeah, let's take a break.
Okay. Thank you.
Okay. Ah. Now what should I do? What should I do? But I've done this.
Okay, so we can resume now and we can like go for the hands-on part. So we will have two hands-on. One, trying to see and try to showcase two possible applications of this kind of problem. So multimodal missing multimodal information on graph data, and we will do that through like an application on the recommendation domain. So the first hands-on, and then to the healthcare domain, and the second hands-on is this one. Okay, as for the Google Colab, you may find it at the tutorials website. It's actually posted with also the PDF of the slides and all the material we use for this tutorial. So I can give you like 2-3 minutes if you want to download the Colab and maybe then like code with me. Like a couple of minutes, no more than that. Okay, so maybe we can start. Okay, so we can start from the first hands-on session on so for the domain of recommendation. And basically here we will see how to run a complete pipeline for for imputation on missing modalities with this kind of domain, and we will consider the approach so we proposed at CIKM 2024, so IPROP. Okay. So basically, so for time constraints, I will not like go through and run all the cells. So, but I will like describe them, and you have all the pointers to then so kind of run them and consider them and run the full column on your own. Okay, so first we so basically clone the repository so that it's so like accessible on GitHub, of course. Then we need to set up so the environment, so with all the other available and useful Python packages. So to be honest, we don't need all the possible packages, so we just need some of them, so which are not already installed into the Colab like notebook here. So once we do that, here the idea is to work with a wide popular dataset in the recommendation domain, so the Amazon dataset. So that comprises many categories of products, and so for this particular case, we consider the office product category. And so basically the multimodal data here correspond to the photographs and the description of the items on the product web page. And what we do here is to first download the dataset, so with this multimodal data, and also the data accounting for the user item interaction, so kind of record, and that we need to use to make the final task. Then we prepare so the dataset, so by means of this command. Then if you don't want to like lose too much time on this cell, you may want to like download the pre-processed version of the dataset accessible here at this other cell, so that you see here. Okay. So then, since the so the process and the whole pipeline, so we need to run, it's a highly GPU dependent one. We may want to so to make sure, of course, so that the instance we are running, it's actually equipped so with a GPU. And then we can start to actually so run the pipeline. Here, what we need to do is to first extract the multimodal features from the item images and description. And to do so, we will use Ducho, so that is like a feature extractor, so that we proposed, and that it's like highly so customizable, and it can be used to extract any kind of multimodal features with so with sentence so kind of TensorFlow, PyTorch, transformer, and sentence so transformers, so many possible types of backend here. And we do that, and we like run this cell here to extract all the multimodal features. And to run Ducho, we need to first set up and write a configuration file, which actually and specifically tells how how to extract the multimodal features from the items. And that's so what it's been encoded here in this YAML based file. Okay, and then we do the extraction, and to be honest, it's pretty fast. It's gonna take like 2 to 3 minutes and no more than that. And we will have the multimodal features, so for the visual and textual so modalities for all the items, apart from those which don't have those two modalities, of course. Okay. Then we want to, of course, run a kind of a recommendation task here. So we want to like split the user item graph into 3 portions, so the training, the validation, and the test set. And we do that by means of this cell here, so that does all this stuff. And so now we have the multimodal features of the available items, so just those. And then we have the user item interaction matrix, which is split into trains, validation, and test set. Now we can actually, so we are ready to actually run the imputation strategies that we may want to use to like complete the final pipeline. So first here we propose 3 very traditional and very simple imputation strategies, so that are the zero, then the mean, and the random imputation adopted in machine learning in general. So through this cell, so you will be able to run so this kind of the imputation, just to compare them with the graph-based ones that we use and that we propose in this paper. Okay. And so this should also be like super fast. So because it's a small data set, and running so this kind of imputation, it's like very simple. Okay. And then what we need to do at this point is to make a mapping. So this mapping is useful because in general, the users and the items that we have in the catalog can be so kind of represented by means of strings or any other alphanumerical values. So we want to map them to a continuous set of numbers, so from 0 to n-1 for the user, and 0 to m-1 for the items. And that's what we do here so with the 2ID Python script. And we do that so not only for the user item graph and the trains validation and test set, but also for the multimodal features we have extracted. Okay. At this point, we are all set and all ready to run the graph-based imputation that we proposed in this paper. So we can run the the neighbor mean as the mean of the nodes from the one-op neighbor. or we can run the okay, so here it's kind of discuss of what I discussed about in the previous slides. Okay, and we can run the neighbor mean here, or we can run the propagation at multiple ops here, so with the normalization of the adjacency matrix. And finally, we can run the personalized so PageRank to have a more complex way of diffusing these available features to reconstruct the missing ones. Okay, here I just reported some code snapshots from the complete code, just to understand what happens under the hood. And so basically, so once again, we see how we so first obtain the item graph from the user item one. Then we sparsify it by means of the top key strategy. And finally, we create a sparse adjacency matrix here, accounting for all the this item so kind of connections. Then what we do is to first load the available multimodal features accounted for the visual and textual modality here, so just two modalities. And then we actually run the neighbor mean so strategy, so that is so kind of pretty simple. Or if we want to go for more so complex strategies, we run the multi-op so strategy, where we actually so perform a message passing with no weights on the item adjacency matrix with the visual and textual modalities loaded in previous time. And here we can also see so what I was referring to in the previous slide. So we first set all the features to a zero values, where we are considering so missing features, and then we do the so the propagation of features at multiple ops, and each time we put back the available features in the proper order and place, as we can see here in this line I'm just referring to here now. And then we save all the inputted features, and we can use them so for the final task. So for the personalized, so PageRank is exactly so the same. So the only difference here is how we compute so basically the normalized adjacency matrix, and that's what it's like encoded here in this cell. And you can take a look at this, and actually so this code so snapshot was taken from the original paper of Diffusion Improves Graph Learning from NeurIPS 2019. Okay, at the end of the day, we have the complete data set of user and items and all the multimodal features. So not only so the available ones, but also the inputted ones with one of the so strategies we considered. Now we are all set to run the recommendation task, and to run any possible model here to see how this perform with these inputted features. Here we chose BM3, so that is a very so kind of recent approach, so that is so pretty known and pretty so well established. So so you can use any other kind of multimodal so recommender system out there. So because the main point of these approaches is that they can be run on top as a preprocessing step to input the missing modalities, and then run any multimodal approach so later on that will exploit and leverage these modalities, and that's it. Okay, and here I also put many possible runnings to actually compare how the final performance is kind of affected by the imputation strategy we used. Okay, and that's it. do you have any questions on this first hands-on session, or should we go further with the second one? I guess we can go with the second one. Okay, so the second one, okay, so let me stop the sharing once because I need to go to that. So the second one is actually like run so for another domain, so the healthcare domain, and still we want to use a very known so kind of methodology to input some missing some modalities in the healthcare domain. So let me go here, and I will show again the screen. Okay, yes. Okay, I guess the screen is visible on YouTube as well. I hope. Okay, so here we consider the task of the healthcare, and we want to make some prediction on the healthcare domain when we deal with multimodal data on the patient side. And for the sake of this second hands-on session, we consider a very popular model, Muse, so dated back to to ICLR 2024. And Muse works by means of the through graph and then bipartite graph in terms of the type of categorization we gave in the previous slides. Okay. So we of course thank and acknowledge the usage of the GitHub code of Muse here. Okay, so we first clone the repository again. Then we download the dataset. So here we are using some healthcare dataset, and in particular the EICU data, so that is pretty known and pretty famous in the literature. However, we couldn't share the dataset in this case. So the version of the Google Colab you will find online is actually a Google Colab completely similar to what I'm sharing now. The only difference is in this cell where it's completely empty. So because the idea is that you need to download the dataset on your own. So because we don't retain the rights to share this dataset, so you need to go through a process to ask and to require that, and they will give you, and you can then run the Colab here to complete the complete session here. Okay, so that's what we needed to do, and also a further disclaimer is that since the dataset is pretty huge, here we just used a reduced version of the dataset, which accounts for just 10,000 patients, if I'm not wrong. So because otherwise the computational time was quite high for the power and resources available on Google Colab. So it was just this, and I would suggest you to have a reduced version of the dataset in order to make it feasible. So running that on your laptop should be fine, and so you should be able to run it for the complete dataset, basically. Okay, then we just installed Python Geometric in this case, as this is the only needed package that is not installed yet on Google Colab. Then we check again the GPU, of course, and then we start with the preprocess of the dataset. So here we actually follow what the authors did in their GitHub repo. So please take a look at it and just refer to it. So what they do was to first parse the dataset to retain the most important information that they want to retain, so from the complete ESU dataset. And in particular, so they just come up and they just consider these possible features of the patients, which they will group together in a certain way to end up with, I guess, 4 or 5 different modalities at the end of the day. So the idea here is that we don't really have some images or some textual so kind of description of the patients. So what we have is a tabular data with many column features, and what they do is to consider just some of these features and to group them together in a logical way, so that this group of features are considered as modalities, and that's how they interpret the problem as a multimodal problem. Okay. So then they preprocess and they keep kind of preprocessing the data, and that's what you need to do to like complete this part. And then they also build a vocabulary for EICU, so because there are many features here so that are so categorical, and they want to like understand and to store in a proper way which are the possible values of these categorical features. Or maybe there are some textual based features which can be mapped to a shared so kind of vocabulary to then use so later on some kind of textual encoder to then so kind of encode them. And then they of course so split the data set into trains of validation and test set, and they split them according to the observation of the patient. So a certain group of this observation will follow into the train set and then to the validation set and then the test set. So it's not like a temporal split. Maybe it would have been better to consider a temporal split, so because it would have been more logical to have so like a coherent split of patients in the previous time and then in a follow-up case. So but here so that's what they do, and we stick so with what they do, but a possible so kind of improvement of this so that would be to consider the temporal information of this kind of data set. And then we can run the train and test of Muse. So we don't really have any other kind of imputation so script here, because as we said, Muse it's a through graph so methodology, and also a kind of a robustify so methodology. So meaning that we don't really input any missing modality. We just make the model robust to the missingness of modality, and that's why the complete logic of this methodology is contained in the script run so during the train part. So the kind of robustification is done end-to-end in the training pipeline here. Okay, so once you run the train and the test set, then so you are done, and you have so the complete set of metrics to then see if the prediction task was good or not. But no particular information on whether the task was pursued in a proper way in terms of the missing modalities is actually given. So we don't really know if the final prediction and the good and so possibly good outcomes so from the final prediction are coming from some particular cases and some particular parts of the model, or the kind of robustification of the model to be able to account for missing modalities. And that's a possible drawback so we consider so later in the so kind of future direction part of the tutorial. Okay, so by taking a deeper look at the code, here we have the forward function of the Muse model, where we have the actual grouping of all these features into logical modalities. And so we have the code, so the lab one, and then the Apache AppSpar modality. And then we have the calling of the GNN function to actually run the link prediction to predict the missing links and make the model robust to the missingness of modalities. So first we can take a look at the encoders for all these modalities, and maybe the positive point here is that the encoders are trained end-to-end in the downstream task. So this is not the same as the previous case we have seen in the first hands-on session. So we don't pre-compute and we don't extract all the multimodal features in a pre-processed way, but we extract them during the training, during the end-to-end pipeline. So the weights of these encoders are actually trained and fine-tuned during the training. And this, of course, could impact in a positive way to the final task so that we want to pursue. But of course, this could increase the computational kind of power of and kind of weight of this model. So we should be careful about that, and maybe we should find a compromise between the two cases. Okay. Okay, so these are all the encoders that they consider for each of the modalities. And finally, we can take a look at how the GNN layer works here. So the GNN layer is implemented as a GraphSage model, where we also consider the edge part. So the message passing is not only done at node level, but it's also done at edge level to also update the edges and not only the node features. And that's what you see here. And in fact, they also have a kind of an update edge here, so to do what I've just said. Okay, and the final forward function of the GNN is first doing is first creating the two views of the graphs by means of an edge dropout strategy, and then because the idea is to then obtain the two versions of the same node features and then contrast them by means of a contrastive learning loss at the end of the day. And that's what they do here in the unsupervised part of the loss function. Well, the supervised one is the same described before, and basically we have we want to make sure that patients which have the same labels can predict one another, and that's what we do in the supervised part of the loss function, and it's encoded in this part of the code here. And finally, okay, and one last thing is that, of course, the computation of the two node views is not done at inference time, but it's only done at training time. So at inference time, we just have the bipartite patient modality graph, we run the GNN, and then we perform the final prediction task made by means of an MLP model here to do the final task of classification. And that's it for the second hands-on session. Do you have any questions on this second hands-on session? Otherwise, we can wrap up and yes.
Yeah, thank you. So based on the data side, you manually divide them into different modalities. So how you group them into different modalities might here?
Okay, it's actually something that the authors do, and basically, what they do is to group some features, coming from the tabular data set at the very beginning, and they want to group so some of these features into logical groups, and each of the group will then account for one modality. So basically, so for example, the age, gender, and ethnicity features will account for one modality, considering the metadata of the so patient. And then I guess that they group the diagnosis and the treatment and the medication into one modality. So and that's a kind of a textual modality. So because they so for each patient they have like a list of medication, and so first diagnosis, then they have a medication and a treatment like resulting to that kind of diagnosis, and that's it. And then the lab values and the Apache observer are other two modalities that they consider at the end of the day.
In general, does the number of the modalities will affect the performance of the imputation?
Indeed, and I guess so that here so you should find a compromise. So because maybe maybe having many modalities would end up in a very kind of representative and highly rich so data set, then resulting in a very rich and very complex model. But maybe having many many modalities would also lead to a too much expressive model that could be like kind of detrimental. So because the model could be very much prone to overfittings, for example. While maybe having less modalities would be better in this case, so the model would be more simple, so maybe it would not be affected by overfitting, but we might lose, and we might be like too much so kind of loose-grained and lose so kind of a little bit of information here. So it's like a compromise. So that's what the authors did. So but we could come up with another so kind of grouping of these features to get all the modalities. Yes, indeed, it's actually a good point. Yes.
Thank you.
Thank you. Other questions?
There is another question from the online audience. So he is asking, so does the information of each modality correct the other modalities in this case, or these modalities are independent from each other?
Okay. Okay. So for Muse, indeed, we have a cross-modal setting because we have a bipartite graph of patients and modalities. So since all the modalities are together in the same graph, indeed, while we perform the message passing on the bipartite graph, we are so kind of reconstructing so some modalities with the other ones so kind of also. While in the previous case, so for the for the recommendation one, we actually have a kind of a intramodal setting because the modality is imputed only by considering the available ones from the same modality. So it's not so like a cross-modal setting in that case.
Thank you.
Thank you. Other questions? Okay. Then I think we either take a pause or we just finish with the very so last part of the tutorial. So maybe we can finish. I don't know. We can close it.
We can proceed.
Okay. Okay. So I will stop the sharing from my computer, and I will be back on this computer. This has been like a challenging stuff to do. Okay, so the slides are here again. Okay, so but I need to share the screen again. Share this one. see. Okay, so can you see the slides or not? I guess that's fine, no? Okay. Okay, so we want to so kind of wrap up a little bit. Oh, no, okay, we need to go to the other stuff here. Okay, so we want to wrap up a little bit. So what we discussed about so during this tutorial, and then maybe try to identify some possible challenges and future directions that we might take to address all these challenges. So what we learned so far. So we learned how to define missing information in missing information in unimodal graph machine learning, and we have seen we have three possible ways of defining it. Then we have seen a taxonomy of approaches to solve and address this problem in unimodal graph learning by means of on-through graphs and then input and robustify approaches. Then we have presented like a selection of three approaches which follow in each of these families here. Then we saw how to define and how to apply multimodal data and multimodal learning to graph data, and that's so what we call so multimodal graph learning. We come up, so we actually presented a blueprint of the multimodal graph learning strategy here, and then we consider two approaches, two kind of kind of representative approaches, so from the recommendation and the healthcare domains. On this lesson learned, we then combine the two stuff to understand how to define missing modalities in graph learning and how to address it by means again of a taxonomy of approaches, so considering on and through graphs, then input and robustification of the model, and then a further dimension just like set for the task of missing some multimodal information in graph learning, where we distinguish between similarity graph and bipartite graphs. And then we have seen like a timeline of growing approaches from the literature, so from the 2020 up to the present time, and we then like consider and presented some selected approaches accounting for some of these domains, and we have seen how they work and the similarities with with previous approaches in the unimodal case. So because they are kind of inspired and they are like a follow-up on these kind of other models. Okay, so what's next, and which are the the challenges we consider here? So first, we have identified a list of possible applications for this kind of setting missing modalities in graph learning. But the question here is that, so could we think about other domains where this setting and these models could be so useful? And the answer is yes, because we have a complete family of models working for the natural sciences kind of family, so that are structured as a graph, and where we have like solutions and methodologies which can be run to perform imputation on the missing values for this data. And we are talking about the molecule and drugs kind of domain, then the proteomics one, and then also AI for the climate. But the point is that all these domains, for the moment, don't really consider a multimodal setting. So the question is, So can we use the approaches we have introduced in previous slide to tackle and address so these problems from a multimodal point of view? And the answer is probably yes, and we will try to see if this can be answered in future direction and future years of this so kind of domain. So that's the first challenge, and how to address it. Then we want to we want to understand which are the advantages and the disadvantages of all the families of the taxonomy we consider here. And so in terms of input and robustify, we have some of them. In terms of input, so we can see that the advantages are that the model are interpretable, so we can actually see which are the kind of reconstructed multimodal features, and we can do a kind of a quality check on them to see if the reconstruction was good or not. While in terms of disadvantages, we can say that maybe it's not that easy to compare the inputted features with the available ones. So maybe this could be a disadvantage. And then in terms of the robustification approaches, we have the advantage that it's better to generalize. So because when we make the model robust to the mixingness of modalities, it's more prone and more ready to account and tailor many scenarios and many settings where we have some missing modalities. But the disadvantage is that here we don't really have some kind of interpretability, because we have a situation where we are not actually considering the node features, and it's not easy to interpret what we did. So maybe a good option would be to combine the advantages of both the approaches to get and come up with a super powerful approach at the end of the day. While for the case of similarity and bipartite graph, we have the following advantages and disadvantages. In terms for the similarity graph, the advantages is that they are quite easily interpretable. So because it's easy to understand how two patients are similar, how two items are similar in terms of multimodal data. But the disadvantage is that maybe this similarity information may be kind of redundant, and maybe we should be so careful to understand how much of this information we should use in place or with the actual information that we already have. And then which kind of similarity to use here? So which is the most suited one to tailor the task so that we are considering? While for the bipartite case, the advantage is to have again an easily interpretable model, which has been already implemented and experimented with the case of unimodal graph learning. So we have like the lesson learned from the unimodal graph machine learning case. But the disadvantage is that it's less interpretable. So it's not easy to understand how to use the node features of the bipartite graph. And then how can we what we should do with this kind of node feature? So that's also a question that we may want to answer in following up to this kind of tutorial. Okay, and then another important aspect to consider is in terms of the evaluation. So how can we fairly and completely evaluate all these models? So we should indeed need some fair and extensive kind of benchmarks to understand how and which models are actually performing better. so basically, putting all these models with the same multimodal feature extractors and the same so kind of predictors in order to be sure that we are not like running an unfair kind of evaluation between them. And also, so we should try to understand if predicting the missing values is actually a condition we need to pursue, or maybe we can just drop them and make the final downstream task and then make the predictions. And that's actually something that these authors in a paper from iClear 2025, so they ask and they try to understand, and that's a pointer I would like to just give to you. Then, and to conclude, we may want to see if we can use some diffusion models to maybe generate back the missing modalities, and that's been done in some scenarios, so like in the healthcare or in the tabular domain, and also for the recommendation kind of domain, and also for the unimodal graph domain, and finally with graphs of foundation models. So indeed we have many so we have so many examples of all this kind of situations, and how to use diffusion models to input missing modalities on graph data, and we may want to use them for future directions of this kind of topic and domain. And that's it. So thank you very much. Any questions, or it's
From the audience? Okay, and there are no further questions from the online audience as well. So thank you for this fantastic talk tutorial. We really appreciate the time and care you have put into this to make it so accessible and informative. And as we mentioned, the tutorial materials are already posted on the link on the ILG website, and please be sure to check them out. And finally, please fill out the tutorial feedback form. And
you're right.
it is at the end of the tutorial slides.
I will share it again. Yes, you're right. It's indeed here. Yes.
Yeah. So if we would appreciate it if you can take 1 or 2 minutes to fill out the feedback form, and we greatly appreciate the feedback you may have. Let's thank Danny again for giving us this great tutorial.
Thank you. Thank you very much again. Okay.
Learning on Graph conference. We have 4 presentations with 15-minute talking time and about 5 minutes of Q&A. The first paper is Exploring Intrinsic Structures of Hyperedges as Point Cloud, and Ligay Zhang will be presenting. The questions you can post in the oral discussion on Slack, and you can ask them at the end of this presentation in the 5-minute slot. I'll be reading up your questions. Thank you.
Hello everyone. My name is Ligay Zhang and I'm from Duke Kunshan University. And this project is in collaboration with Professor Dongmian Zhou, who is also my supervisor. And this project, we revisit the hypergraph neural network. But to begin with this presentation, I would like to give a brief review of hypergraph notations. So a hypergraph is something similar to a graph. It can be denoted by like vertex set, edge set, and the vertex attributes. And the only difference is that for a graph, we have like bidirectional connection. Each edge consists of 2 nodes. But for a hypercorrelation, as you can see, one hyperedge can contain multiple nodes. So this is the only difference. We transit from the adjacency matrix to an incidence matrix. And in general, there are 2 common ways to define the message passing on hypergraph, because message passing basically is essential for graph representation learning. So researchers have been thinking of how can we define similar message passing on a different topology. So in general, there are 2 ways, or like most commonly, there are 2 ways to do it. The first is called the vertex-centric HNN, which basically like the clique expansion over here. So it's difficult to directly define the message passing between the node because there's a hyperconnection. So one potential way, as you see, is to expand the topological connection by fully connected subgraph. And then you basically transform the problem into a GNN problem. And we can use the old method like GIN, GAT on the hypergraph data. And there are another category called vertex hyperedge HNN. So basically, this is a 2-step message passing. You first pass the message from the node to the edges, and then from the edges back to the node. And it can be visualized by this star expansion over here. So basically, what people see is they use these virtual nodes. Basically, they view hyperedge as a node attribute. And you first pass from the actual node to virtual node, and then from the virtual node back to the actual node. So here's a summary. So this VHHNN is what most people use nowadays, I think. So basically, this is the message passing framework. And I would like to give a brief summary of the development history of hypergraph learning. So actually, learning on hypergraph is not a new topic. It is proposed a long time ago. Even before the era of deep learning, people have been discussing about high-order learning problem, like in 2006. And not until 2019, there's the first HGNN paper and HyperGCN. So basically, they said, okay, now we are transiting from graph neural network to the so-called hypergraph neural network. And they give some naive solution to this learning problem. And then in the following 2 years, there are many more works. Basically, they investigated different architecture to implement HNN. Just like after GCN, people investigate GAT, GIN. So similar things here. There are many architectural proposals. And in most recent 1 or 2 year, people have been thinking about some problem that we usually found in graph learning, like over squashing, over smoothing, or heterophilic hypergraph. And there are some recent advances in these domains. But in our work, we don't want to, we don't want to discuss about what kind of architecture we want to propose. I want to ask a more fundamental question. So, as you can see from previous slides, most methods often approximate the topological structure of a hyperedge by a graph topology. And this is true for both clique expansion or star expansion, as you see over here. So although there are many variants of HNN, what they do is they always have a graph approximation of hyper correlation topology. So what we're trying to answer is a fundamental question. Can we build a hypergraph neural network that directly operates on hypergraph without viewing it as a graph? So the intuition we propose is that we say we can view hyperedge as a point cloud. Well, point cloud is usually in dimension 3, but here is like a generalized high-dimensional point cloud and with implicit connection. And our solution is also very intuitive. We use a non-Euclidean kernel and translate over the hypergraph, just like in CNN. And we perform hyperedge feature extraction. In doing so, we do not require any heuristic assumption of the hyperedge structure. So this is like an intuition of our model. So in CNN, what people do is that, so CNN has a structured grid-like data, and we have a kernel. So the kernel basically slides through the image, and for each of the receptive field, it gives you some updated representation. And here, we try to do similar things. So as you can see, for hypergraph, we don't have like this square-like kernel. We have something different, but it also has some rigid structure. And instead of sliding through the image, what we're proposing is the kernel slides through each of the hyperedge and conduct the feature extraction of hyperedge. So this is like the high-level intuition. And so first question is, what about the kernel? How do we generate the kernel? So basically, we define a kernel generating loss function as follows. The idea is that for each of the kernel points, they actually correspond to the cell in the CNN kernel. We want the kernel points to be distant from each other, but also not too distant from the origin. And so it basically has a shape like this, a very structured shape. And in fact, this kernel generating function is not first proposed by ours. I remember in 2017, in the kernel point convolution paper, they first proposed similar kernel generation for a computer vision task. And last year, we also had a paper called Hyperbolic Kernel Convolution, where we generate similar kernel idea to hyperbolic space. And after that work, we're basically asking if this is still going to work for a different topology like hypergraph. So this is like the motivation behind it. And yeah, and for this loss generating function, we can actually prove that the kernel generated forms the shape of a regular simplex. But actually, I think it's not very important. It just have a rigid structures. And in this slide, this basically visualizes the procedure we do the feature extraction. So in the paper, we separate it into 3 subsequent steps. In step 1, the kernel initialized at the origin first translates to each of the hyperedge center. So this step is kind of like the sliding process in CNN. And the second and third step, it corresponds to the aggregation functions in CNN. So the second step is basically, so let's look at this equation. So this pool and aggregation is what CNN usually do. And in our design, the step 2 is actually a generalization of the blue part. But you might wonder why like okay, so here we have a kernel point transformation of each node, but what about this correlation part? It seems that in CNN, we don't have this correlation. And the reason is because, as you see, in CNN, each of the node cell overlap with the kernel cell. So we know there's a one-to-one correspondence between the node and the kernel. But for hypergraph or hyperedges, as you can see, when we translate the kernel to hyperedges, there's no direct overlapping between the kernel points and the node cell. Therefore, in order to generalize the CNN into the non-Euclidean structure, what we do is we conduct a soft generalization. So here we say, okay, we compute the transformation for all of the kernel node pair, and we just take a soft aggregation and basically let the model to decide which kernel best overlap with which node. And the final step, this is just the red part of a CNN where you have some max pull or average pull. But what we do here is simply we take an average aggregation. So as you may perceive, this is a very intuitive generalization of Euclidean CNN. And there are some notes I would like to point out. So in the first step, this zk tilde is the kernel point. So in the training procedure, we first initialize the kernel point at the origin. And this is a step before the training. So the kernel generating function decides the kernel initialization. And this is not a part of the model training. And second of all, so how do we decide like where we translate the kernel? So basically, we use the hyperedge centroid, which is calculated by the node members. And so in each of the iteration, we translate from the origin to each of the hyperedge centroid. That is how we define the translational movement. And so as you may perceive, this sounds like an iterative implementation, but our current code base uses a pure tensor operation. And what we do is that we take the HGNN framework and we add a residual connection. Then we basically replace this aggregating function by the feature extractor that we propose. And that's basically what we do. And for this method, there are some problems. Like, as you see, this kernel generating function does not lead to uniquely defined kernel. But our hope is that, okay, so you might have different kernel initialization. We hope the final output will be invariant under different initialization. But this is just our hope. Probably, I think in hyperbolic metric, you can have some invariance. But in the Euclidean metric, we didn't find invariance. So what we want, if we cannot have invariance, the best we can do is to analyze the stability of the model output under different kernel initialization. And the overall intuition is that if the kernel is smaller in radius and number of kernel points, we usually have a more stable output results. And also, when we compute node kernel correlation, there are many ways to do it. You can compute the distance or the inner product. And what we found is the attention-based correlation is more stable, as you see in the second equation. And this is some results we have. We reached several SOTA performance, some benchmark, but I think this might not be the most important results. I think instead this ablation is more inspiring. So what we do is we did a careful ablation. We replaced the aggregator in HGNN by our CAMP aggregation, and it seems the performance improved quite a lot. I mean, usually beyond 2% in most of the settings and most of the configurations. And we also had some other evaluation, like how the number of kernel points influence the performance. And second of all, we discussed about like the stability, right? We said that if you use attention-based correlation, you're guaranteed to get more stable results. So we draw some box plot. As you see, this green plot is corresponds to the attention-based method, and it generally provides a more stable results. And so this is consistent with our theoretical analysis. But for the future study, we want to tackle with some limitation of existing implementation. So as you can see, the per epoch training time increases with respect to the kernel sizes, and it can be a lot slower than some of the simple method. If we do it, currently we do it in tensor operation, it is also memory consuming, because basically we need to replicate number of kernels copies and translate them to each hyperedge simultaneously. This is quite memory consuming, but of course we can do it in an iterative manner where we use a for loop. But in doing so, I guess there will be some challenge in computation time. And also for the future study, we want to implement some hyperedge related benchmarks. And because what we're presenting here is a general feature extractor, so we want to test if we can integrate it into more diverse backbone models and see if it bring benefits in general. This will make the work more solid. And that's all. Thank you.
Any questions from the audience? I don't see anything online. Okay, so for the interest of time, let's move on to the next one. Thank you so much. The next oral presentation is any conjunctive query, graph neural networks for answering queries over incomplete knowledge graphs. Thank you so much.
Hi everyone, my name is Krzysztof. I'm a PhD student at the University of Oxford, and I have the pleasure to present the work that I've done jointly with Shinie, Michael, and Ismail on answering queries over incomplete knowledge graphs. And as a quick recap from yesterday, knowledge graphs store information in a structured way. Their vertices represent known entities, while the edges, the relations between them. And it is well known that knowledge graphs suffer from the incompleteness problem, meaning that they miss some of the true information. And this can be a result of either poor generation, but also potentially the relations may seem redundant. For example, if someone won an Oscar, then they surely must have been nominated for it. In this work, we are interested in answering queries over knowledge graphs while accounting for this incompleteness problem. So consider a question, where was the director of Oppenheimer born? It can be represented as the following first-order logic query, and also as this graph. We will call this graph a query graph. And what would be the answer here? Well, it would be an assignment to the free variables of Q, which is just X in this case. That makes this query satisfied over the complete knowledge graph. And in this particular example, this answer would be X mapped to London, as that's the birthplace of the director of Oppenheimer. We may also be interested in recovering a certificate that validates that this is indeed a correct answer, which would be an assignment of Y, being a person who directed Oppenheimer and was born in London, and we can indeed get it by taking Y to be Christopher Nolan. So currently, query answering is phrased as a ranking formulation, as a ranking problem, in which we are given the observable part of the graph G, and also a query. And here we will restrict ourselves only to existential first-order logic queries, being some propositional formulas with some of their variables existentially quantified. We will use this arrow notation to represent tuples of variables. And since each such query can be decomposed into a disjunction of conjunctive queries, from now on we will only consider conjunctive queries, so queries which are conjunctions of literals. And coming back to our formulation, the output for this problem is a ranking over all possible answers, being the assignments to the free variables. And since here we only have one free variable, this will be just the ranking of entities from our knowledge graph. And once we have this ranking, we identify the correct answers. Here is there's just one, but in general, we may have more. And, well, we use some standard ranking metrics to evaluate the performance. However, we claim that this formulation is not enough. And to understand why, let us think about what would a perfect query answering engine would be. So first of all, it should be able to account for the incompleteness problem, as we don't want it to miss any information just because it's not a part of the knowledge graph while it is a true answer. Secondly, while it does so, we would like it to be efficient and applicable to queries of arbitrary structure. And in particular, currently, most of the CQA methods are restricted only to tree-like queries, which are queries whose query graphs can be represented as trees. And even simple formulas that don't satisfy this, so we call them cyclic, are beyond the scope of processing of the existing approaches. And we wouldn't like our perfect query answering engine to have this limitation. In a somewhat similar fashion, we would like it to be able to solve queries with multiple free variables. So far, I've shown you only examples with one free variable, but we can ask a question, who directed Oppenheimer and where were they born? Which is a perfectly reasonable thing to ask. And, well, coming to the first limitation of a ranking setup, what would be an answer here? What would be the output? Well, it should be a ranking over all possible answers, which in this case are tuples, pairs of variables. And as you can see, as you can imagine, if we grow the number of free variables in this query, the size of the output grows exponentially, so that quickly becomes computationally infeasible, just by the construction of the formulation of the problem. And lastly, we would like to be able to classify answers as true or false, because right now we only get some relative ordering, and we're not really asked to tell which answers are correct, which are incorrect, just the ordering matters. The problem with such a model is that it most likely does not exist, as deciding the satisfiability of arbitrary Boolean formulas is a known NP-hard problem, so we cannot combine points 2 and 4 just by what complexity theory tells us. But using the magic of machine learning, we may hope to approximately solve this problem or almost satisfy all of the conditions listed above. So with this motivation, we reformulate the query answering task as a classification objective and propose two different problems. In the first one, we are given the observable part of the knowledge graph, a query, and also a potential answer. And our goal is to say whether this answer is a correct one. Again, remember, in the complete version of the knowledge graph. And here we've already seen that this answer is indeed correct, so the output should be yes or true. In the second, harder problem, query answer retrieval, we no longer assume that this candidate answer is provided to us, but indeed are asked to find one or decide that no correct answers for the given query exist. And as we already know here, the model should return X1 mapped to London and X2 mapped to Christopher Nolan, as that's the only answer to the given query. All right, so does this reformulation help us a bit? Well, first of all, it reduces the problem of our output increasing exponentially, because in QAC, the output is just true or false. So that's a very simple thing to encode. And also in QAR, the output is supposed to be an assignment whose size grows at most linearly in the size of the input query. So we no longer have this exponential blow up resulting in, well, with the number of free variables. All right, so we have these tasks, and how do we solve them? Well, we first of all notice that both of them can be viewed as a search problem. As consider an example query and the associated QAC and QAR instances. What does it mean for an answer X mapped to A to be a correct one for the query? Well, it means that if we set X to A, then there exists some assignment to the bound variables of this query, so to Y1 and Y2, that make both of the literals satisfied. So instead of asking, is X mapped to A correct answer, we may ask, is there an assignment to Y1 and Y2 that makes all the literals satisfied under the assumption that X is mapped to A? And in this way, instead of asking this classification problem, we basically turn it into a search problem when we search for a correct assignment that will make this query satisfied. And similar for QAR, for the other task, here we are interested not only in this in the assignment to the bound variables, but also to the free ones. And if we find one that satisfies all the literals, then we can just return its restriction to the free variables, and that will be a correct answer to the query. All right. So how do we solve this? We propose NECQ, a GNN-guided search engine that iteratively searches for assignments and tries to improve them to maximize the number of literals that they satisfy, hopefully finding one that will satisfy them all. The framework consists of two parts. The first one is a link predictor that informs us about the structure of the complete knowledge graph. And this link predictor is a function that takes a relation type and a pair of vertices and returns the probability of these entities being in the given relation. So using the link predictor, we can reconstruct the complete knowledge graph. In particular, we use the threshold of 0.5 to say whether a fact is true or not. So if the link predictor believes that the probability of something holding is greater than 0.5, we consider it true, and otherwise we consider it false. So that's how we handle incompleteness. And how do we handle search? Well, we have some graph neural network that acts as a search policy and iteratively selects new assignments as we explore the assignment space. How does it do so? Well, it uses a computational graph that incorporates information about the input query, about, well, the information from the link predictor pi, current assignment, and also some internal hidden representation that the GNN stores. Then this computational graph is passed through our GNN, which updates its internal representations, and also derives a distribution from which we sample the next assignment. And once this search step is done, we repeat the process, updating the embeddings and getting new assignments ready. Right. So the two things I need to still tell you how we do it is, well, how we construct the computational graph and then how the GNN processes it. So starting with the graph, it incorporates information from 4 sources, from the query, the link predictor, the assignment, and some embeddings. So starting with the query, for a given query, our computational graph will have 3 different layers. The first layer, the one on top, will correspond to all the terms mentioned in the query, so all constants and variables. Then the second layer will denote all the possible assignments for the terms. So for each constant, we will have the trivial assignment of this constant to itself. And for each variable, we will have all assignments to all entities known in the knowledge graph. And this will be connected to the appropriate terms. And finally, in the last layer, we will have so-called literal nodes, which will represent the literals in the query. And these will be connected to the assignment nodes of all the terms that they mention. So for example, the one on the right, R of xy, will be linked to all the assignment nodes of x and y, as these are the terms that it mentions. Right, so that's how the query defines the structure of our graph. And now moving to the link predictor. The link predictor is used to inform us about which assignments we should take and which ones are favorable to be taken. And it does so by 2 different edge labels. The first set of labels that we call potential edge labels intuitively asks the question, does it ever make sense to consider an assignment? So consider this edge, for example, between the literal R of xy and the assignment y to c. Our potential edge label will answer the question, can the literal Rxy be satisfied when we set y to be c? And if we look at what our predictor believes, indeed, if we set x to d and y to c, there is an edge of the right type going from d to c, so we get the label of 1. And that's the first part of the link predictor. And right now, since we don't want to start the search from scratch at each step, we also need to include the information about the assignment somehow. So first of all, we mark all the assignment nodes that correspond to the current assignment. This is just a binary label to distinguish them during message passing, nothing fancy. And then we also devise a second set of nodes called light edge labels. And while potential edge labels were more for initial guidance to guide the search into more favorable parts of the assignment space, light edge labels are responsible for iterative refinements so that we satisfy more and more literals as the search progresses. And coming back to our example, when the P label answered the question, can the literal be satisfied when we set y to c for any x? The associated light edge label will ask, is this literal satisfied when we set y to c for the current assignment to x? So in other words, if we change our assignment marginally so that y is mapped to c instead of what is mapped to right now, is the literal satisfied? And in this way, by using those light edge labels, we can check which assignments make, well, more and more literals satisfied, and then hopefully we will find one that satisfies them all. And that's the whole structure of the computational graph. We also have embeddings, which are just vectors of, well, some dimension, which are stored in the assignment nodes. And, well, how the GNN processes this thing. First of all, we start with the assignments, with the embeddings in the assignment nodes. We propagate them to the literal nodes, where this information gets aggregated, and then it gets sent back to the assignment nodes, which, well, are updated based on the message that they get. And once we finish this process, we repeat this on the other side of the graph. So we propagate information to term nodes, do something with that, send it back, and update the assignment nodes. Finally, this gives us the next set of embeddings, but also we can use it to, using another projection, to generate logits from which the next assignment is sampled. And more precisely, for each variable, we take the logits that we predicted, apply softmax, and then from this distribution, we sample the next value for the variable in the next assignment. All right, and since I'm running out of time, obviously, once we have search, once the search completes, so it executes for a certain number of steps, we take a look at all the assignments, we rank them somehow, and we basically evaluate the probability of them being correct assignments using fuzzy logic, and also using the predictions from our link predictor. For training, we use reinforcement learning to train our network on very small instances. And in particular, we use a reward being the number of satisfied literals. And while doing so, we hope that it will be better it will manage to generalize to queries of arbitrary structure. And to test that this is indeed the case, also with our motivation of being able to handle arbitrary queries, we devise a data set of large formulas that consists of formulas with up to 20 variables, including up to 3 free variables, which is much larger than what's been considered in the literature so far. And it's large enough to the extent that actually none of the existing approaches can be applied to our new benchmarks. So skipping to the interesting parts, the only baseline that we actually could test against was SQL. And yeah, that's what everyone likes to see, right? Our method beats the baseline on all the splits that we consider. And if you look at this table, the performance gap becomes more pronounced as the number of free variables increases. So to see whether that's the case, we consider 2 separate cases. We consider easy instances, which are questions that have some answer in the observable knowledge graph, so that it can be found by classical algorithms, potentially. Oh, and I should have said that both these methods have the time limit of 60 seconds here. So in the easy case, SQL, if given infinite time, should get 100% everywhere, but we impose this time limit to make all the computations somewhat, well, reasonable. And the second case are hard instances, which are questions where we need to infer some additional information that's not present in the knowledge graph to answer them. And as you can see, in both cases, NECQ produces non-zero numbers, which means it finds something. In the hard case, SQL by definition fails completely. But what's interesting is that even in the easy case, so when the answer is provided in the knowledge graph, NSEQ consistently outperforms SQL in the cases where there is more than one free variable, which suggests that it's just a very efficient engine for these cases that can compete with classical solvers, even very optimized classical solvers, and that its combinatorial efficiency is quite high. And also what we test is that the two components I was talking about, so the link predictor and the search policy, are actually quite independent from each other. And the motivation behind that is that if it's really the case, then we could take one strained GNN search policy and for any knowledge graph, take a relevant link predictor, plug it into our framework without the need of retraining the GNN, and then have a query answering engine for that. And while we don't want to overclaim anything, the initial results are quite good, showing that this is indeed the case, and we can replace the GNN trained on different data sets with minimal loss in performance. And well, this suggests that this may be extended to some foundational model for query answering over knowledge graphs in the future, but that's for future work. And as I'm already out of time, I'll just leave this slide here, and thanks a lot.
Thank you. Any questions from the audience for this one? Meanwhile, the next presentation is by Haggai, so he'll set it up and wait for some questions. Thank you. Thank you.
Okay, it's me again. Yeah, so I'm going to talk about this GL equivariant meta-networks paper, which is a part of the weight-based learning kind of direction that I was talking about yesterday. And this is joint work with Mo Potterman, who was at Berkeley at the time, now at OpenAI, Derek Lin, who was at MIT when we wrote the paper, now at OpenAI, and Yoav, my student, Michael Bronstein, Stephanie, many good people. Okay. So let's start with understanding what is parameter efficient fine-tuning. The idea is that you take a neural architecture with some trained parameters, theta, and then you would like to slightly change those parameters in order to do something better. So for example, you want to train on a refined data set or something like that. That gives you a new network with parameters theta plus delta, where delta is some kind of delta of parameters in parameter space. The main thing that we want to do in parameter efficient fine-tuning is to be efficient. So this reduces the memory that we need to use, and we will see some numbers and you will understand. It gives us a way to store efficiently the fine-tunes, and it also acts as a regularization mechanism. So by far, the most common variant of parameter efficient fine-tuning is low-rank adaptations, which we will call LoRa from now on. So the idea is that instead of just having W matrix as a delta, we will parameterize the delta using a low-rank multiplication of two matrices, UI and VI. So for each W in our model, WI, we will add UI times VI, and those UI and VI are low rank. Okay, so instead of having M times N parameters, we will have R, where R is the rank, times m plus n. And when r is small, this is significant. Okay. So there are other parameter efficient fine-tune methods. Dora is kind of similar to LoRa. Cron A is another method that uses Kronecker product instead to parameterize the adaptation and so on. But LoRa is by far the most popular one. Okay, so what does it mean to learn on LoRa's? We take a fixed fine-tuned pre-trained model, and then we take a data set of those UI, VI matrices, and we would like to learn on top of them all sorts of stuff. We will see some examples soon. Okay, so essentially, we train only on the LoRa's, okay? Only on the UI and VI. The original architecture and weights are kept on the side. So what can we do with learning on LoRa's? One thing we can do is to try to assess the accuracy of a model on some data set. Instead of just running, evaluating the data set, which can take a lot of time, you can train a network that takes these low-rank adaptations and gives you a number that says whether it works well or not on some data set. You can also do other stuff. For example, you can try to understand data membership. For example, ask whether some data point was a part of the training process of the LoRa. And this could be interesting for, testing whether your test data, for example, was a part of the training or so on, similar things like that. Can also get information about other things like how many points were trained using the LoRa and so on. Okay, so one important thing in this slide is to see the differences in the sizes. So in this particular case, we have a model with 3 billion parameters. The LoRa parameters are only 1 million. Okay, that makes it much easier for us to process them. And then learning on LoRa's model that we will see in a few minutes, there are 7 million parameters. Okay, so we kind of discussed why to learn on low-rank representations, but maybe another main motivation is that we cannot really learn on top of those huge models, like 175 billion parameters, for example. This is a huge input. We cannot really do anything with it. But on LoRa's, because of this reduction in the dimensionality, we can do something. The other thing is that LoRa's are actually available online. So you can find LoRa repositories, people put them online. This is, as I said yesterday, it's a new data type that is out there, and it's interesting to apply machine learning to it. And of course, we can do some useful things with it, like we mentioned. Okay, so when we want to come up with models, with architectures for LoRa's, we want to take advantage of the parameter efficient structure, right? One thing we can do, very simple thing, is to just multiply those two U and V, and we will have a huge matrix, but then we don't get the benefit of low dimensional input. So we would like to process U and V not in the multiplied form. But if we choose to do so, we introduce new symmetries. Those symmetries are kind of a new type of symmetries that the geometric deep learning community didn't really work on till now. Those symmetries are multiplication by invertible matrices. So essentially, if you take U and V, and you take UR and V minus transpose, you will get exactly the same delta, right? Or an invertible matrix. So again, along the lines that we mentioned yesterday, if our function, the function that we're trying to approximate, for example, the accuracy of those parameters, theta, if those functions are invariant to some transformation, we would like the model to be invariant as well. So this implies we would like MetaNet, which is our name for those LoRa consuming networks. They should be invariant as well. Okay. So what we did in this paper is to propose several architectures for learning on LoRa's. We'll go over them quickly now. And we start from the very basic ones. Okay, so we have a list of naive architectures that we used, just, in order to understand whether they work already and we don't need to, come up with fancy architectures. So the first two architectures are just applying MLP on transformer to the concatenation of U and V, right? This is probably the most basic thing that any of us would have done if we wanted to try something fast out of the box. So what's the problem with it? Main problem is that we don't have GL invariance, right? The O invariance here is the orthogonal group, which at certain cases, it's enough to be invariant to this group. So we don't have any invariance in this case. And we will see that this approach doesn't work. Another naive approach is to apply an MLP to UV transpose, right? So in that case, we fix the invariance problem, right? Because we multiply them, so there is no ambiguity anymore. But we need to process those huge matrices. And we will see that this approach works pretty well, but doesn't scale. Okay? And then we have several approaches that are, we call efficient symmetry aware architectures. So let's go over them. The first one is MLP of O align. So what does that mean? So when you have symmetries, one way to deal with them is to align your input to some fixed templates. So think about the graph, for example. If you get an input graph, you can have like a random graph on the background, and you can try to align your graph with this random graph for any input graph. This will create alignment between all the inputs. And then you can apply any model. You don't need invariance. This takes care of the invariance in a sense. Okay? So in our particular case, we want to align according to GLR, the invertible R by R matrices. But this is difficult. So we align with respect to a subgroup, which is the orthogonal group. Okay, so only for orthogonal matrices. And this is pretty easy to solve using, this is essentially a problem called the Procastes problem, which you can solve with doing SVD and multiplying the outputs of the SVD in a certain way. So this is solvable. So we have this approach, which is essentially to canonicalize the inputs, right? And this is a general approach to dealing with symmetries. We have another approach. In this case, we don't take as input the U and V matrices. What we do is to take only the singular values. And the reason we did it is because there was a previous paper by Salama et al. That showed that you can actually predict the dataset size from those values. From invariance point of view, what we have here is some kind of an invariant feature that I brought from home, right? So I know that those features are good for something. I don't need a network to learn those features. I will just use those features as input and apply some MLP to it. And in certain cases, that's fine. So this is invariant, but one can show that those are not expressive. And the last thing is something that we call GLNet. So GLNet is a fully equivariant architecture, what we did is to derive the linear equivariant layers for these symmetries. We also had to derive or to suggest new nonlinearities. So you should think about it. Standard nonlinearities in this case wouldn't work because they are not equivariant to this action. So you need something else, and we use some kind of nice gating mechanism. This is something that is usually done in cases of continuous groups. So, as I said, we analytically characterize all the GAL equivariant linear maps, and we design those gated nonlinearities. And we also come up with the way to create an invariant feature in the end. You can think about it as some pooling mechanism. Okay. So let's talk about the data and the experiments a bit. We have three main experiments. The first one is on the Celeb A dataset. Second one is on CV AI LoRa dataset. Those are open source fine-tunes that we just downloaded. It's not like synthetic data. And we also have fine-tunes of Qwen and Llama 3. So let's see what we can do with those. So first, we tried to predict the clip score of a fine-tune of this diffusion model. Okay, so the clip score, it measures the alignment between the image and the prompt that you used in order to generate the image. Okay. Okay, so what we can see here is first that I don't have the table, but all the models work pretty well in predicting the clip score. So R squared is close to 1. And you can see visually that for specific prompts, our results make sense. So you can actually use this model in order to select fine-tune, like LoRa fine-tunes that are related to what you want to generate, right? Another thing we tried is on the Celeb A dataset. So this is a nice dataset. It consists of many celebrities, different images of those celebrities. And we created a LoRa to each one of those. And then what we tried to do is to predict properties of those images using the LoRa fine-tunes themselves. So for example, whether the celebrity has eyeglasses or is he wearing a hat, or so on. Okay? And we can see that we can do that pretty well as well. We also tried to predict data membership. That means to predict whether certain subset of the data was used for training this particular LoRa or not. This was harder, but we still had some positive results. Definitely, we need to work on that more. We showed that loss and accuracy are pretty easy to predict. So in this particular case, we have a data set of fine-tunes of Llama, and we are trying to predict the ARC score. Okay, so we also tried, one of the reviewers told us that we need to try on real data sets, and this is a very good comment. So we tried our model on just LoRa's that we download from the internet. So we downloaded it from a website called Civit AI. And then we tried to predict the label of the LoRa given the LoRa weights. So it's either vehicle or building. And we succeeded with 90%. That means that we can actually work on real data, not only, data that was generated for this particular paper. Okay, so lastly, I want to talk about scaling, and we have two experiments here. The first one is how do you scale to larger models? So if you scale your LLM, for example, you are going to scale your LoRa's as well, right? So in yellow here, you can see what happens to the naive method that just applies multiplication to U and V and then applies an MLP. And this explodes pretty fast, right? And on the other hand, you can see our GLNet approach, which scales pretty nicely to 175 billion parameter models. The other type of experiment that I would like to discuss before I finish is zero-shot generalization to other ranks. So let's say that you trained the LoRa's on the LOL model on LoRa's of certain rank. Would they generalize to unseen LoRa's? And the answer is that those models do generalize pretty nicely. They generalize between different ranks. They even generalize between different models sometimes, which is kind of nice. Okay, so future applications could be to use these kind of things for very fast LLM and diffusion model evaluation, for detecting harmful or illegal content in fine-tunes. As was suggested earlier, this could be used for interpretability. And we also think that there might be an opportunity to come up with actual generative models for LoRa's. So think about the opportunity of just, writing in plain text what you would like the LoRa to do, and then generating a LoRa. Okay, so those models would probably need LoRa models. Yeah, and that's it. And I'm happy to discuss and answer questions as always.
Questions?
Hi, thank you very much. That was very cool. I don't know if I get it, but aren't you missing a symmetry in the LoRa's?
Which one?
So if you, yesterday you explained that if you permute between the layers, then the answer should be the same. And that's not something that you capture here, right?
That's right. Let me clarify. This is actually a very good question. So what we do here in this particular paper is to fix one particular model in the background. And that kind of fixes the permutations. But one can think about a more general use case in which you would like to take as input LoRa's from multiple models that are not aligned, and then you will have both internal GLR symmetries and external P symmetries from the permutation rules.
Then it's kind of surprising that because you did have some transfer to other models, right?
Yeah, but only within the family.
Okay.
So, the next generation is probably a fine-tune of the previous one. So the kind of alignment is stable.
Right. Okay, thank you.
Any more questions? Okay, there's one online question as well. Yeah, I'll just read it out. What is the limit of I think he's trying to write explainability of the zero shot of LLMs? Is the generalization difficult in instances where the data is poor? Does the equivariance break?
Does equivariance break?
Yeah.
We saw very
sorry.
nice results for zero-shot adaptation to different ranks and fine-tunes like different models. So in that sense, we are kind of data efficient. Yeah, I'm not sure that I really understood the.
Yeah, the word was explicability. What is the limit of explicability of the zero-shot LLMs?
Not sure I fully understand what.
Yes.
Yeah, but they can reach out to me offline if they want.
Okay. Any more questions from the audience?
Yeah, no, thanks for the nice talk. So I was wondering, like, what is the ideal approach, like, if I don't really care about running time? And I thought it would be like just basically add the LoRa update to the weights and apply like a meta network like we know. And that would be like, so I could, so why do I, so I guess, have you considered that? Just like,
Yeah, this is essentially one of our baselines. So not adding, but just multiplying the U and the V and then applying an MLP or transformer to that.
yeah, but like, but instead you could just apply like a meta network, right? That would take care of
Yeah,
the invariances
but
in
those models
in
are huge. You don't really want, unless you really want to do that, you don't like. There is no good reason to process this whole thing if you can predict it only from the LoRa, right? Because in this setup, you assume that you have like a fixed model, underlying model, and then the only thing that changes are the LoRa's.
Yeah, I just wonder if you try like on some small like
You cannot,
networks.
like, I don't know of any weight space network that can consume models this large nowadays.
Okay, yeah, thank you.
One more question.
Thank you for the talk. To follow up on this, do you see any other advantages of learning on LoRa's instead of multiplying them together, except for efficiency, obviously?
Currently, it's mainly efficiency, but this is a big thing. It's not something that we can.
Well, yes, surely. But is there any other?
It seemed like for most of our experiments, the MLP applied to UV transpose works well, but just takes a lot of time and doesn't scale.
Right, sure. Thank you.
Any more questions around? Actually, I have a quick question to follow up. So you mentioned LoRa's are also good for regularization in LLMs. What do you think would be the way to evaluate whether learning on LoRa's is, helping with regularization when doing prediction?
I'm not sure those two things are related. So we mean by regularization the fact that you cannot like change the model too much because you're constrained to change in a very certain way, right? But I'm not sure that we can do anything interesting with it with LOL models. Perhaps, I don't know. Perhaps we can, I don't know, do some self-supervised learning on top of LoRa's and then seek for patterns in embeddings or something like that. I'm not sure. I need to think about it.
Okay, thank you. There is a follow-up in Slack. So the question earlier was, what is the limit of explicability of this zero-shot of LLMs? And is this generalization difficult in instances where the data is poor? Now, the follow-up is, sorry, it was an IAX related question. Yeah. I'm not sure, but let's just have them follow up with you directly.
Okay.
Thank you.
Thanks.
Okay, thank you so much, Hagai. The next presentation is a position paper, Beyond Euclidean, Foundation Models Should Embrace Non-Euclidean Geometry. Thank you. And this is by Rex Yank.
Great. I'm happy to be here, and thanks everyone for attending the session. And here I'm happy to talk about our recent work, position paper on beyond Euclidean foundation models to embrace non-Euclidean geometry. And throughout this talk, I will also reference some of our recent papers at KDD and Europe's that are related to this topic to further validate some of the ideas. Okay, so we'll get started. As a lot of you guys are interested, here we are mostly looking at the embedding geometry of a large-scale foundation model, a model that has been pre-trained on a large amount of unsupervised data that are going to be used for various downstream tasks. And a lot of times people have looked at the model architecture, right? So that's the foundation model on the left. How do we design a highly expressive model architecture, such as transformers, to perform various tasks. Make sure the neural network is expressive, right? And this positioning paper is basically trying to argue that there's something in the middle that is still also very much worth exploring, which is the embedding space, right? You can have the most powerful foundation model architecture in the world, right? That is super expressive, that can model any kind of function that you want. But if the embedding space in the middle, right? If the embedding space geometry is limited in the sense that it cannot represent the underlying geometry in terms of metrics such as inner product, which is being used in various autoregressive models, right? Then the downstream task is basically being bottlenecked in between, right? So basically that's what we are hoping to look at in this paper, right? And we argue that it's not just the model that needs to be expressive, but also you want the embedding space that can represent the underlying geometry of the data, and combining both of them, that will give you the best model you want for whatever foundation model setting that you're looking at. Okay. So I'm trying to motivate this in one modality, which is natural language, but this kind of argument is not just limited to unsupervised text data, right, on the text foundation models, but also various other modalities such as images, graphs, time series, various things that people want to build foundation models for. Okay, to start with, let's look at why this might make sense, right? So why underlying geometry between tokens, let's say in the text modality, is going to give us the motivation for designing foundation models in non-Euclidean geometry. All right, so under the hood, right, these kind of foundation model a lot of times is following this kind of autoregressive paradigm. So let's say given a kind of a sequence, right, that's from a tokenizer, right, which is what most of the foundation models are building based on, right, and we want to predict the next token in a sequence. So now the tokens can be patches of images, can be words, can be nodes in the graph, and so on, right? Under the hood, what's happening is that we're going to compute inner product, right? We're going to compute some kind of distance metric, and then the ground truth, right, the true next token is supposed to have a larger inner product, or a kind of closer distance to the current embedding of the current token, right? So that's what like for example, this simple example, right? If the sentence go until the word the, and if the next word is above, then it's better true that the representation of the embedding for the above is close to the word the, right? After at the last layer of right before your softmax. Okay. Right, and if we look at these transitions or these next token distribution in the underlying underlying distribution of your unsupervised text corpus, it's very obvious that they are kind of unequal, right? They're not created equal, right? There are words that kind of are very prevalent, that can happen in every single sentence, and then there are words that are very specific, right? There are words that are a particular, let's say, Alzheimer's disease or whatever, right? That kind of happen in a very particular context, and that doesn't happen a lot, right? But on the other hand, there are very little of these words that happen very common, and then there are large amount of words that are kind of rare and very specific, right? So this directly bring us to kind of investigate what the underlying geometry of these kind of next token relationships are, right? So think of this, in this case, this kind of geometry is represented by the relation between different tokens. So every node you see here is basically representing a token, and their unsupervised corpus. Right, and we can use metrics like hyperbolicity to test what does the underlying geometry looks like, right? Hyperbolicity. So this is a normalized hyperbolicity values here, right? So 0 means it's a perfect tree, right? And then the closer it is to 1, that means the more cycles this relationship actually contains, right? And if we do that in the context of a foundation model, such as a large language model, this is what we have observed. So just to make it clear, what happens is that this relationship graph is very difficult to construct because of the trillions of tokens that are being used in this unsupervised text corpus. But what we can do is to use a proxy, right? We can measure this value of hyperbolicity within the embedding space of the large language model. So we're going to look at the last layer representation of your LLM, and then we compute the hyperbolicity by replacing the shortest path distance in the original definition with the embedding distance, right? For example, Euclidean distance. That's where the current Euclidean geometry, where the embedding lies in, right? So we can do that for a bunch of language models, and we can test these hyperbolicity values across various different data sets from like arXiv, CommonProj, GitHub, and various types of unsupervised text corpus where we use to train foundation models. And the result is that these hyperbolicity values are kind of small, right, close to 0. This is a reference. Perfect tree is 0, as I said. So 0.1 is kind of considered pretty small, and that generally confirms our hypothesis that the language distribution is actually kind of hierarchical. Okay, and here's some further investigation. So on the right, on the left, you can see kind of a plot of a large language model token frequency. Sorry, the count of the token versus the token frequency, right? So this is a very clear trend of power law, right? On one hand, we can have tokens that appear very little, right, with very little frequency, but there are a lot of them, exponentially many of them, right? And on the right-hand side, there are tokens that appear very often, right, but then there are very few of them, right? So it's a typical power law, right? And then you would imagine that given this kind of power law, those tokens that are kind of very high in hierarchy, or those tokens that appear very common, right? They should be embedded in the middle, right? Because they need to be close to everything else. Right? They need to be in the middle, right? So that's what the norm diagram shows also, right? Whereas you have exponentially many of these tokens that kind of appear less often, and they typically have larger norm because you have larger space. You can put it like in whatever specific place for that token, right? So because it doesn't need to be close to everything else, just need to be close to whatever that can appear in the context. All right. So what happens when we try to this kind of embedding strategy, right, in a Euclidean space? So we start with tokens that are very common, and then we embed things that are less common, right? Because it's a kind of a power law distribution. So as you go less and less common words, there are many, like more and more of them, and in this case, exponentially many of them because of the power law. Okay, and if you try to do this, so far this is good, right? But then problem emerges as you try to embed more and more of them, right? And the problem just basically is that when you try to embed a lot of these words that are uncommon, right? They tend to be very close to each other just because there isn't enough space to be able to embed them together. And that's bad because these tokens that are less common, they kind of get too close to each other, right? When things get too close to each other, your inner product no longer differentiates their score, right? Their logics. And as a result, you can't really distinguish different words in that particular context, resulting in hallucination, right? So this could be one of the reasons why hallucination can happen in these kind of foundation models. And in essence, we want the model or we want the geometry to satisfy two things in this particular foundation model, right? So one thing is that those common tokens, right, they should be close to basically everything, right? Reasonably close to everything, because this common token can appear in all kinds of contexts, right? But on the other hand, we also want those tokens that are less common, right, but then exponentially many of them, to be sufficiently far apart from each other, right? If they are too close to each other, basically you can't distinguish these tokens, right? So that's the two criteria. These are the two criteria, and the argument is that in the Euclidean space, you can't simultaneously satisfy both criteria, right? You can satisfy the first criteria, right, by making sure your common token is in the middle, and then and then have everything else around it, right? Like that. But then you violate the second criterion because these tokens are too close to each other, right? On the other hand, you can satisfy the second criteria, right? You want to make sure that all the tokens are far away, right? Just by like placing things next to each other, making sure they're far away. But then you know that in that case, the common token is probably going to be too far away from some tokens, right? So and therefore violate the first criteria. Okay? So this is kind of the argument why in this kind of case, foundation model really needs beyond Euclidean geometry to be able to have an embedding space that can model this kind of underlying token distribution that is just not non-uniform. Okay, and in practice, there are many kind of geometries, and they are all good at modeling different kinds of underlying distribution, right? So it's commonly observed, right, as in what my previous example shows, text and image typically exhibit negative curvature, right? It's scale-free, hierarchical kind of pattern. But then there are also a lot of scientific domain that can exhibit positive curvature, things like phase kind of data, robotics, kind of pose. There's a lot of things that are cyclical, molecules, right? So a lot of different kinds of geometry can be suitable for training different kinds of foundation models in different contexts. Okay. So therefore, our position is that the development of non-Euclidean foundation models is essential for effectively representing, modeling, and analyzing complex data structures and relationships in these real-world applications, especially in the context of large-scale foundation models where unsupervised data have their own underlying distribution that is not being perfectly modeled by Euclidean geometry. Okay, so there are different advantages to using this non-Euclidean geometry, right? First of all, it has better representational capabilities because of the expressiveness inherent in the geometry, right? So pairing an expressive architecture with that geometry is going to give you the maximum benefit, right? And on the other hand, you can also get benefit in terms of adaptability. So different geometry can fit different types of data better. So creating a geometry that is flexible, with variable curvature, or product curvature, curvature space, those can be generally beneficial as well. And then finally, we can overcome some kind of scaling law issues, right? And nowadays, a lot of people are saying that pre-training kind of plateauing and so on, and using an alternative geometry can potentially kind of break that kind of plateau and let it be able to continue to scale. And that's what we're also kind of working on, right? And I just want to briefly mention that there's a kind of common misunderstanding because there are things like Nash equilibrium, Nash embedding theorem, and stuff like that, right? That basically says any n-dimensional Riemannian manifold can be embedded into a Euclidean space, right? But I just want to make sure this is kind of clear, right? So what this means is that it's embedding manifold, right? When you embed manifold, the distance is not the distance that is inherent in the Euclidean distance, right? So you can embed, for example, a sphere in your Euclidean geometry, but then when you try to compute the distance between the 2 points with that embedding, right? It needs to be on the sphere, right? It needs to be that geodesic. But in actuality, when we actually train neural network, what you're going to do is in the product, right? And that's kind of Euclidean distance, right? So that's kind of the mismatch, and that makes things like Nash embedding theorem not really applicable, right? So what we really want is be able to model these kind of geodesics on the space, such that you can benefit from all these geometric properties of the embedding space. Right. All right. So a key issue here is distortion, right? So I want to say, like, given these kind of phenomena, right, that we observe kind of in practice, embedding those things in the Euclidean geometry has the key issue of resulting in distortion. So we have some details about the theorems that will be applicable in this use case, but I'm not going to expand due to the lack of time. But distortion basically means that your underlying data, right, the distances required in your underlying, unsupervised data in your pre-training is kind of distorted in your embedding space when you compute, for example, Euclidean distance or whatever metric distance in your embedding space. And we want to minimize this kind of distortion, right? We want the embedding space distance to exactly reflect the underlying data distribution, right? And there are this kind of trade-off that kind of enhance the position because you need increasing dimension is a way to kind of minimize or make the distortion smaller, but the cost is actually pretty big. The dimension is actually required to grow kind of near quadratically if you want to kind of decrease the distortion, and that's probably not a good approach, right? The more effective approach is probably to design better geometry and design your metals in that geometry such that you can be a lot more efficient at it, right? So here's an example, right? Just a very synthetic example, right? We have different structure, and if you were to increase the dimension to big, the efficiency is actually very low, right? So every kind of structure here is best embedded in some kind of geometry. Like for example, tree. In this case, it will be hyperbolic geometry, right? You can easily get like very small distortion with very small number of dimensions, right? And in cycle, in this case, the best fits would be spherical geometry, and if it's a kind of combination of both, right, in terms of topology, then you would want to use some kind of product space between these, right? So it's crucial to pick the right amount of geometry, and if your geometry is right, you don't need that many dimensions to make it like much smaller in terms of distortion. Okay, and here's the same, right? So distortion versus the amount of dimension needed, and you can see that if you pick the right geometry, right, the training will look a lot better, right? And yeah. So this is what we want to mention, right? So how do we kind of develop this kind of non-Euclidean geometry given all these things, and we want to talk about how we kind of can address limitations in capturing these kind of token structure and capturing this kind of trade-off, and also modeling different modalities, right? So there's a position paper, so I'm not going to talk about the methods in much more detail, but I would want to say, what would it take for us to, finally get to a point where we can build very expressive, high quality non-Euclidean foundation models to state of the art, right? And the first strategy is to, do fine tuning on top of existing Euclidean foundation models, right? We already have a lot of good open source foundation models, especially in the text and image domains. And these are typically Euclidean, right? So an easy way or a straightforward way is to think about some, for example, parameter efficient fine tuning, right, as one way, such as slow rank adaptation, in order to fine tune and move this model into the non-Euclidean geometry, right? There's one possibility. There are also other possibilities, like for example, doing knowledge distillation. Can we build a more efficient small model that is in non-Euclidean geometry that is doing distillation from some extremely big Euclidean models, and we can do that to improve the efficiency and performance of the model further. Okay, and we can also benefit from transfer learning and things like that. So again, these are mostly kind of adaptation of fine-tuning kind of approaches, and it's also related to the previous talk. And related to that, we also have a NeurIPS paper, kind of spotlight paper at NeurIPS 2025 called HyperLoRa. So what we basically did is to look at the natural language modality, and given this hyperbolic or hierarchical structure of text modality, we built a low-rank adaptation method based on this intuition of mapping things to the hyperbolic space. So we take an existing Euclidean model, and then we add these hyperbolic adapters through three different operations: the exponential map, logarithmic map, and some kind of fully hyperbolic operation, in order to kind of mimic this behavior of adding kind of additional weights in order to map things to the hyperbolic space and have a loss on that, right? And we demonstrated its performance on top of a bunch of large language models in various reasoning and mathematics tasks, and showing a lot better advantages, especially on like much harder, like this particular data set that represents like much harder math questions. Okay, let's see how much time. Okay. And the other kind of approach is to, of course, to pre-train from scratch. This is also reasonable in some cases, especially like scientific foundation models. It's a lot more complicated because you want to kind of basically transfer every single model component in Euclidean space to some kind of special geometry. But we've actually have already done some of that as well. And and the option 3 is to build some kind of hybrid architecture. We can have some Euclidean components. We can also have some non-Euclidean components, such as hyperbolic, such as spherical, various kind of geometry. And we can use something like a mixture of experts here to kind of combine them together so that we can leverage, benefit from multiple kinds of geometry when solving a particular problem. Right? And we've actually also did some of that in our preliminary work, which is also published at University of 2025 a few days ago. It's called Hyperbolic Large Language Model, HELM. We actually did exactly what I just mentioned by converting some of these components of transformer to the hyperbolic space and build things like multi-head latent attention, which is common in many state-of-the-art LLMs such as DeepSeek. And we also use a mixture of curvature experts, so we can combine different kind of curvature model architecture that's in different kinds of geometry, and then pick the right expert for a given input context. We demonstrated improvements at 100 million and 1 billion parameter sizes on top of DeepSeek v3 and Llama 3 as well. We are currently kind of trying to scale it to 8 billion and 32 billion. Of course, it's a lot harder in the academic context, as you can imagine, but this kind of ongoing effort as well. So I think this has a lot of promise. So I just want to mention that we can build better infrastructures for non-Euclidean geometry as well. So this is kind of a library called HyperCore, which we have recently released. It's basically a comprehensive library for building things in hyperbolic geometry with all these kind of state-of-the-art components that are relevant to foundation models. So we've actually have built like very comprehensive modules for all the components, like from MLP, GNN, CNN transformers, VIT, fine-tuning, LoRa, CLIP, even GraphRag, all these kind of applications and comprehensive modules, operations for everything, building everything kind of fully in the hyperbolic space. And we kind of release them. This is using this framework, it's very easy to build something like a low-rank, hyperbolic version of Vision Transformer, hyperbolic version of CLIP. All these models can be RAG. All these models can be built on top of our library. Okay, and the usage is pretty simple. On the left is a Euclidean version of the PyTorch, and on the right is the hyperbolic version. So it's basically an exchange of naming. Everything else is like PyTorch. Okay, so yeah, so that concludes my presentation, and thanks everyone for listening. Just want to thank my collaborators from different institutions.
Thank you. We have time for one quick question only. Is there one from the audience? Okay, great. We're at time for the award ceremony, so we'll get started on that, right? Handing over to you.
Okay, thank you guys for sticking around for the closing remarks. Okay, so just an overview of the mission of LOG. So hopefully in the past couple of days, you saw the latest advances in graph and geometric machine learning. A big part of LOG is also building a supportive community with truly accessible to all, free to attend virtual option and a hybrid conference with many local meetups. And a big part of LOG since its founding, of course, has been the review quality with monetary awards and accountability to incentivize review quality. So we saw, just an overview, what we've seen the past few days. We saw 4 awesome keynotes, 3 awesome tutorials, a bunch of orals, poster sessions, and local meetups. Oh, okay. Okay, great. So we had 6 local meetups around the world. Thank you so much to the organizers of these meetups. And so looking ahead to next year, please feel free to give us any feedback. You can scan the QR code here on the slides. We'd love to know if you'd like to become a committee member for future logs or become a reviewer. So please just keep an eye out for a public call for committee members and reviewers. And if you'd like to submit papers, host tutorials, just let us know. We really welcome your feedback. Okay, great. So let's get to the awards. Okay, I'll start with the best paper runner-up. So this was Learning Kronecker Structured Graphs from Smooth Signals by Changhao Shi and Gal Mishna. Do we have either of the authors in the audience for their award? Great. Congratulations. Oh, yes. Okay, okay, got it, got it. Okay, we could still take a photo. Great. Thank you. Yes. Applause. And then for best paper award, we have short range over squashing. So this was by Yakov Misheyev, Yonatan Sverdlov, Talamir, and Nadav Deem. Do we have any of the authors here in the audience? Great. Let's do a picture. Great. Thank you. Next up, we have our AC awards. Let's see. Okay, so area chairs. So we are really appreciative of our awesome area chairs. So they had a big batch of papers. They engaged with their duties, with the bit of the reviewers throughout the process. So we really appreciate these awesome reviewers. So our ACs. So that's Bastian Rieck, Xiaowen Dong, and Robin Walters. Can we just get a round of applause? And then honorable mentions here. We have Tess Smith, Joey Bose, and Mikhail Galkin. Thank you very much. Great. And then finally, we have our top reviewers here. We have Corey Scott, Tamara Kukumidz, Igor Kravchuk, Pierre Borgna, Simone Antonelli, Pascal Velka, Nikhil Madan, Tarana Yunazian, Yakub Binkovsky, and Joel Matisse. Great. Thank you. Thank you so much for your service and your contribution, and we'll contact you individually about the monetary rewards. Okay, and finally, we have our most active virtual participant award, so really awesome participation in the Slack channel. So that's Rafael Artenano. Oh, great. Yeah, so thanks so much for actively attending and asking these awesome questions. We're pleased to offer you a complimentary registration for the next in-person log conference and hope to see you there. Okay, so that's everything. Thank you all so much, and we'll see you next year.
Thank you so much. Please take some time to fill out the feedback form, please. We'll really appreciate it. Thank you.